Okay. Welcome to my dungeon. I want the bite of your neck. Oh, are we on? It's Halloween. There's the pumpkin, the magic pumpkin lantern. My name is Marko Rodin, I hope. I'm going to open with, I don't know, we'll find out together. Okay, I can't tell what I'm looking at. There's a bee, and it looks like a rainforest. It's an old book, very, very, very old. Someone went to a lot of trouble to compile it. It's excerpts, scriptures from the Bahá'í faith. All praise to the unity of God and the honor to him, the sovereign Lord, the incomparable and all-glorious ruler of the universe, who, out of utter nothingness, see, that's been the big topic. What's a lot of the people who follow the flower of life and 𝘗𝘵𝗲's research. Who is that here? 𝗵𝗲, who's a big supporter, who was talking about the tiny space in the heart last night? Viola and Lisa and Giselle and many other people, they talk about that very much. And in explaining the number 9 last night, we said that 9 was always above 0, vertically above it, which was very significant. It's the apex. Out of utter nothingness hath created the reality of all things, who from naught hath brought into being the most refined and subtle elements of his creation, and who, rescuing his creatures from the abasement of remoteness and the perils of ultimate extinction, does that apply to any of us here? Hath received them into his kingdom of incorruptible glory. By the way, when glory is put into the scriptures in the text, we don't know, but I'm telling you about it, that is the translation into English of the word Baha. There's a glottal stop at the end that lengthens it, so it becomes Baha. Anyway, it's actually the Aleph. But anyway, that's the most great name of God. But the translators, they were teaching, so they weren't worried about mysticism. Nothing short of his all-encompassing grace, his all-pervading mercy, could have possibly achieved it. How could it otherwise have been possible for sheer nothingness to have acquired by itself the worthiness and capacity to emerge from its state of non-existence into the realm of being? It's a cool quote. It's very appropriate because we're talking about how there's an agency, an invisible hand behind everything, and how it brings creation into being, how everything is, how this is a handiwork, and and it's been fashioned. And because we live in this world, I claim we can reverse engineer it and harness all the secrets of creation. Okay, what am I missing? What have I forgotten to say? I'm going to say thank you, John. Thank you, Lisa. We're at Humankind, @humankind.com. What else? Tonight's supposed to be a very big special event. That kind of is supposed to be earth-shattering. So tonight's event, when me and John were originally talking, I slated for myself Tuesday, Wednesday, and Thursday. But me and John, we have forever. And Lisa, we can do this anytime. And so we have 2 honored presenters tonight. They have the entire evening, as long as it goes. Last night we went to like 2 a.m. God help you all. Those presenters is Tony Bell, Anthony J. Bell, and Rune O'Flanagan. They're Irish. And I believe in leprechauns. I believe in fairies. I believe in angels. I believe in, who else? Trolls. I believe in everything. Not that I've necessarily met them or known them, but I've had a few amazing experiences. With what they're sharing and what they say tonight, they believe that it will redefine what quantum mechanics is, quantum field theory is. Phil Du Bois wants to ask some questions. Kyan Willman wants to ask some questions. Greg Volk wants to ask some questions. I have questions. We've prepared them. Randy Powell has some questions. Randy will be presenting tomorrow night from 7 to 9, no, yes, 7 from 9 p.m. So expect his presentation tomorrow night. I'll probably be from 5 to 7 tomorrow night presenting. When I present, I'm going to try and, Randy I think is going to be covering about primes. He's done primes into the thousands. He's done it to his hands, fingers have been bleeding, showing how when you square a prime, it makes a 3D, actually 4D hypersphere torus. They spoke last night, they're going to be speaking heavily about the circuits, but I didn't want to burden us how I define how those circuits actually have a numerical pattern as you go through the size of the tiles and how you can map those circuits. Everyone has their own unique language and way of describing these circuits and how they work. My goal is to define these circuits to make a correct Rodin coil, showing a twist and inversion as it goes through the center. There's so much more that matters when you're trying to create free energy over unity and get rid of friction and parasitics. And the math does that. It gets rid of entropy or noise.
Recording in progress.
So I'm not sure. We'll ask Tony if he wants the people asking him questions or if he wants them to wait till the end of his presentation. If he's allowing people to participate simultaneously, then we'll bring in Greg Volk and Randy and Kyan and Phil. So we'll see what happens. I've handpicked these people. There's a few people in the chat room that I've allowed to ask questions. And when they do ask questions, if we bring it in from the chat, we'll enter them in. We'll actually bring in their video. And then when we're done, we'll take them out. So John will handle that. Have I missed anything, anybody? No. There is a little bit of refreshments, a little bit of jelly beans and stuff. This is very challenging for me. I am learning, not just learning. I don't even have the capacity, and I know all of you are very patient. That we're dealing with people. I'm glad they're not plugged in right now so that they can't say they're not. Okay, but we're dealing with the most brilliant mathematicians in the world. Everybody you're seeing, one way, form, or another. And the definition of brilliant, I'll leave up to you. Okay, let's go.
Yay!
Thank you. Tony. Keep talking, Tony, till he pulls you in. You have to keep talking. Keep talking.
1, 2, 3.
A little louder. A little louder. For my hearing.
In Xanadu did Kublai Khan a stately pleasure dome decree.
Yay!
Can you hear me? Then I guess you can.
I have a request, though. You're worried about feedback. What's giving the feedback? My mic? If I mute it, will I get rid of the feedback? Is it me?
I got you. Just go ahead and just keep going.
Okay. But I'm because my hearing's not good, make Tony as loud as you can. Thank you. And just ignore me, everybody. I'm going to rest under a shady tree. Okay, all yours. Tony, you're on.
All right. I'm not too clear on the technicalities, Lisa. Most of the presentation needs to be streamed from the screen. How do we do that?
It's just share your screen.
Oh, thanks for the pillow.
Just go ahead and hit share down the bottom, and then it'll pop up into my view, and I can actually advance it further.
Okay.
Title slide up front in the center.
Oh, is that his slide up there?
Yes.
And do you know when to change it?
Nope. I only have 2 slides, so we're good. Let me know when you're sharing, and then it'll pop up on my end.
Oh, there's Janet.
Yeah, it's mine.
It's a beautiful picture of her.
Isn't it?
Mm-hmm. Janet, everybody, for your information, got her PhD at almost late 70s. She was very proud of it, her PhD. She was a librarian and a mathematician. And she was a doula, helped people transition to the next world. That type of doula, I don't know the exact name. And people don't know what I'm talking about, but usually when I say this, but there's certain humans that are pillars of support for our over unity, free energy, alternative energy, out of right field, from the side door, scientists, inventions. And she was a pillar of support for anybody and everyone. Okay, I'm done.
Yeah, that's right. Actually, this work this work was done in that we did here was done in 2 houses. One of them was Janet's house in Hilo in Hawaii, and also in Hilo Public Library, where she would leave me in the morning. And the other one, the other house it was done was in Ruan's house in Dublin. And so these people were very kind people to me, and looked after me, and talked to me, kept my spirits up, and made the whole thing worthwhile. So Janet's no longer with us, but I will never forget her for that. And now on the screen sharing, really we should have taken care of this.
It says you started screen share. Is it actually? It's not coming up on our end.
He says that the green screen, we don't see it. We've lost all of the video.
I can't tell what you're looking at. I have a thing called your screen sharing is paused. And if I say resume, nothing happens. And so
we see you again now, but we did not.
Yeah.
So maybe we'll start again now. So try to go to your green screen. I'll tell you if it comes on. Yes, it's slowly loading. Give it a minute.
Now, if I go like this, do you see it going back and forward?
Yes, we did, and it's spontaneous. It's working.
Okay. All right, so then we're in good shape. We can start.
Wait, wait. As I always tell everybody, nobody gets out of this submarine alive. Tony, tell me some of your happiest days. What's ICS? I'm looking at you created a software. What did you do for that organization?
Well, I was a person who was very inspired by neural networks when I was an undergraduate, and I got really into it before it even took off. And so I became a neural network researcher, and I worked in the top neural network research lab, really, which was Terry Sinofsky's. Well, Terry Sinofsky and Geoff Hinton would be the two ones. You haven't heard of Terry because Terry's flying under the radar, but you heard of Geoff Hinton because he's on TV all the time. He's the godfather of AI. And so I knew all those guys growing up, and I worked in that area. And I worked out an algorithm called independent component analysis, which Geoff Hinton told me that he had programmed in MATLAB in 24 characters. He said it was so short that a monkey could have written it by accident. So I wasn't sure if that was a compliment or not. Anyway, that was a one-layer neural network that you can use for separating out signals, any signals really, audio, brain scans. It's been used on cosmic microwave background. Anytime you've got a bunch of sensors and you've got and you want to know what's hidden in them, and the sensors are picking up mixtures of things, then you can use that algorithm to find the little hidden small special signals in it. And so that was the thing which I'm most well known for, is that I was not the only researcher in that area, but I developed the first gradient descent objective function based approach to it. Maximal likelihood or information theoretic approach, you could say. So yeah, then I worked. What's that?
Oh, I was stirring I was stirring my drink. God, I always get in trouble for that. I'm sorry.
And when I was at the Salk Institute, I met Rowan of Flanagan, who's going to be talking today as well. And we had spent many long hours discussing everything under the sun, just like I did with Janet, actually. And yeah, I moved to Berkeley, worked in theoretical neuroscience, got interested in maybe too many things, you might say. There's a lot more than academia to be interested in. But one of the things I'm interested in, of course, is the Rodin lattice, and it was Rowan that turned me on to that. And I think I share with Marko the idea that there are numbers, there is matter, and there is spirit, you might say. And we don't experience each other's matter, really. Well, depending on how you look at it, we experience each other's spirit. I think the experience of spirit is the primary experience. Matter is really a kind of a descriptive thing. You know, it's like you do some experiments and try to talk about what the numbers tell you. That's matter. It's not a primary thing. So whatever you want to call the primary thing, I think it's completely fine to call it spirit. And if you believe that that numbers are primary rather than descriptive, because we use numbers all the time in our descriptions, but I think what Marko believes is that numbers are in fact primary, that numbers are in fact spirit. And that sounds crazy to many people, but it makes complete sense to me, just logically, really. I don't think you have to be religious to believe that. It's a matter of semantics. If you adopt the semantics I just laid out, then numbers are spirit. So when Marko says those things, I believe them. And when he says he's found some pattern in the numbers that is spirit, I'm interested, you know. I don't need to know whether it's true that he's going to cure all diseases or build a UFO propulsion system. No, that's quite fun and exciting. That's enough for me to be interested in it. But of course, it wasn't me that discovered this. It was Rowan, my friend, who will be speaking here. And I don't know what he, well, I do know what he thinks about some of these things, but Rowan's also believes that it's important to find the patterns that underlie the universe and that they could be simple. He's worked on really complicated physics, string theory and things like that. And he's like Greg, he's maybe a little disgusted with the way some of the physicists go about their stuff, and believes that, you know, that we're on the lookout for simplifying principles. And that's what we would share, and that's how we set off on the quest to find what was the physics in the Rodin maps, if there was any, because Marko was claiming it, but we needed to know for sure. So what this talk is about the physics that we found. It's only a little bit of physics. I wouldn't want to say that it's you know, epoch making, but it is some physics. It is actually some physics. It's meaningful to a physicist, even if he doesn't believe the other things. So I'll go to, can you see this second slide? You can see this page here. You guys can see that? I can't hear anybody. Am I just talking to myself?
No, we've been hearing you all this time. They'll fix
Okay,
it.
good.
We heard everything you said, and yes. I think
Okay.
maybe we were being muted just so you didn't have any static in the background.
Okay, good. And can you see these 12 points? Yeah?
Yes.
Okay, so this is the outline of the talk, and I don't know how long it will go. It could go quickly or slowly, depending on how much Rowan interrupts or how much questions we get or where we take it. I'm perfectly happy to be interrupted, by the way. And I'm perfectly happy in a free-for-all situation. So feel free to question me. The structure of the talk I laid down in 12 points, and I'm not just going to go through it. I think I'll just go through the points rather than read them out. We're going to talk about the 2D Rodin grid and lattices and tori's that we didn't really get to yesterday. Yesterday we mostly talked about the numbers. Then we're going to talk about the 4D grids. We're going to talk about Rowan's formula for the 4-dimensional Rodin grid. We're going to see if there's some physics on the grid, and we're going to find out that there is something that looks like physics on the grid. It's a Klein-Gordon equation. And the Klein-Gordon equation is the mother equation of relativistic quantum field theory. It's a very simple equation, but if something is obeying it, that something in some sense has got what they would call Einsteinian or Minkowski space-time in it. And it also has, in some sense, matter and radiation, or what you would call matter and force interactions in it, because the Klein-Gordon equation is the equation for bosons, which are the things that carry force around between matter. Like the clearest one is photons, but there are other ones like gravitons, if they exist, and other exotic ones that you don't see very much, and then the ones that fly around inside the nucleus, the gluons. Of course, those equations are all quite complicated, but the basic Klein-Gordon, they all share this basic Klein-Gordon structure, and that's what was the first physics that we found in the Rodin lattice. And then obviously, because the Dirac equation, which is the equation for electrons and for matter, is the equation for fermions, which is the second family of particles. So two families of particles in physics, fermions and bosons, at least in quantum field theory. Anyway, that particular account of it. And they're very nicely related to each other. The differential equation for fermions, the Dirac equation, is kind of like the square root of the differential equation for bosons, which is the Klein-Gordon equation. So once we'd found the Klein-Gordon equation, which was the bit that was done in Janet's house, by the way, probably at about 3 in the morning, with a nice humid summer Hawaii, you know, insects buzzing outside the window and mosquitoes trying to get in and stuff like that. And so that was something that I discovered on the basis of trying to find well, I'm kind of giving the whole talk. Maybe I should go through the actual points. But anyway, then we when I went back from Hawaii to Dublin, Rowan and I tried to find the Dirac equation in the structure, which was the obvious next step, and we applied some, well, Ruadhan applied some basic mathematical proof type logic to the Clifford algebra structures that I was urging him to use, and we got a Dirac type structure out of that as well. So then we discovered the two main kinds of pattern of dynamic of particles, and also the Minkowski space-time structure in the Ruadhan lattice, which is, you know, pretty amazing, actually. I mean, it's one of those things that's like, you know, it's like a what the hell type thing, you know? What is it? It's a what does it mean type thing. It doesn't immediately tell you how to build a UFO or cure all diseases, but it's definitely a thing that would make you stop and think if you understand those things. So let's go to the discussion of those points. Where are we? Here. And now I have to fly back and forward between different screens. I have to do that a lot. And here we are. Now we can blow that up. And we can make it like that. And we can get rid of, oh no, let's not get rid of that. Mouse wheel blows it up and moves it. Didn't have so much time to prepare this, and we've never given a talk on this stuff before. So this has been done on a in Krita with the pen interface, which I can use to scribble things if there's a need to draw things in response to questions. So the basic idea, the starting idea behind this whole thing is to find a consistent labeling of a discrete four-dimensional space. And by consistent labeling, we mean the kind of thing that we see in point 1 here, which is where you have like a number which tells you where you are, and you've got 8 numbers which tell you all the directions that you could go in a discrete grid. And that gives you 9 numbers altogether. And that's why Mod-9 arithmetic is the structure which talks about four-dimensional space-time. Well, space, let's say 4 dimensions first before we say space-time. And if you were just to look at the 2-dimensional space-time, which would be 1 dimension of space and 1 dimension of time, you would have 3 possible ways to do this in a consistent way. And this is Marko in his Fountain of Numbers talk, which is was one of my favorites, actually, 2019. Here he is showing 3 different Ruadhan toruses. And the basic thing I'm going to describe, so if you ask how many ways are there to label a 2-dimensional space in the way that I just described, where you have 1 number for the where you are and a set of numbers for the direction you can go. Well, in a 2-dimensional space, you can only go in 4 directions. So there are several ways to do it. In fact, there are 3 ways to do it, and they're called the 𝘗𝘳𝘅 1, the 𝘗𝘳𝘅 7, and the 𝘗𝘳𝘅 4. And so there are 3 ways to, there are 3 Ruadhan toruses, so to speak. But if you ask for a 4-dimensional space rather than a 2-dimensional space, those 3 collapse into only 1 solution. And the way to think about it is, imagine you took these toruses, these donuts, and you sliced them on the outside and turned them into flat grids instead. And then you basically, they're like slices of toast, basically, and you just stick them in the 4-dimensional toaster, and they fill out the space of the 4-dimensional hypercube. And there's only 1 way to do that, and you need all 3 of those things to do it. And so at the top, I show the the basic number pattern of the 3 shear. These are, if you were to look at those 3 different toruses that he showed there, they would look, and you were to look at like a little 3 by 3 patch on them, then it would look like this. And you can see that it has the numbers that we talked about yesterday, 1, 2, 4, 8, 7, 5, you know, and then 1, 2, 4, 8, 7, 5 going in the opposite direction. And then 6, 9, 3, 3, 9, 6. Well, 9 and 0. We used 0. I use 0 because I'm a computer scientist. I think that's really, you know, basically, I have no opinion, ideology about it, other than the fact that I'm really used to having 0. So 6, 0, 3. And so if you look at, say, this one, which we've called xt, and this one we've called zt, you can see that the 603 here and the 603 here are sandwiched in between the 1, 2, 4, 7, 5s and the 5, 7, 8, the 1, 2, 4, 4, 8, 7, 5s and the 5, 7, 8, 4, 2, 1s. They're sandwiched between those, but with different slippages, right? So this is the 1 above the 6, whereas here there's the 4 above the 6, and here's the 1 below the 0, whereas here's the 7 below the 0. So the top row and the bottom row have slipped a little bit compared to the middle row in these 3 examples. And that's the only difference really between the 3 spheres that you see, the 3 toruses that you see Marko talking about here. So instead of having them as toruses, we've got nothing against a torus. We can make a 4-dimensional torus, and we can make whatever we want later. Let's just start with a grid. So we're going to take those 3 toruses that we've sliced open, turned into these 2-dimensional grids, and we're going to start sticking them in the 4-dimensional toaster to make the 4-dimensional Rodin grid. And then just one little point about this. If you want to know, is this the only way to consistently label a space? It's not, actually, and Rowan found the other way I'm not sure if he worked it out himself or he asked ChatGPT, probably both, actually. But I've only read the ChatGPT solution he sent me. And there are 2 solutions. There are 2 ways to do this. The interesting way, well, actually, maybe I could show you the, oh, I see. I have to have it like that before I can slip sideways. We can look at one of Rowan's discussions with ChatGPT, and we'll be doing that a fair bit. Here's one of them. Imagine a tessellation of 4-dimensional space-time with tesseracts. A single cell of the tessellation has cubic interactions with 8 others, left, right, up, down, forward, backward, next, and previous. We want to label every cell with an element of a group containing 9 elements. We can pick a reference cell and label it with the identity element, which is 0 in the grids we've been looking at. And now we associate moving in a certain direction to a neighboring cell with the multiplication of the symbol and the origin cell by an element of the group, yielding the labeling of the destination cell. Going 1 cell to the left and then 1 cell to the right, and so on for other dimensions, should yield the label in the starting cell, i.e. the labeling should be self-consistent. How many ways are there to do this? You know, you can spot a logical mind already. Okay, so GPT says, well, there's 6,561 ways to do that. 9 to the 4, and proceeds with the proof. Rowan comes back, yeah, but how many inequivalent groups can be used to produce a consistent labeling for which each cell neighbors 8 cells, all with different labels, which are different to the labeling of the central cell? And consistent means that, you know, when you have a 0 somewhere in the middle, it's going to be the same there as it is everywhere else. There's a 0. And the answer is 2. So there you go. We've got GPT-5 Pro is costs $200 a month. I'm only using GPT-5 Plus, but Rowan's got more money than me. So he's got the best AI in the world, reasoning for 5 minutes and 8 seconds. And it says, there's only 2 ways to do it. Up to isomorphism, the only groups of order 9 are the cyclic group C9 and the elementary abelian group C3 cross C3. So the cyclic group C9 is mod9 arithmetic. That's Marko's world, right? That's what we've been dealing with. The elementary abelian group C3 times C3, to some extent, that's Greg Volk's world, because yesterday he was talking very enthusiastically about having -1, 0, and 1 be and that is essentially what C3 is. It's you get three symbols, and so that second solution, I won't go through all of the things that ChatGPT says there, because it wouldn't really help. But the basic idea is that there's two solutions, and actually I added this on. This isn't something that Rowan wrote. I added this on to the GPT thing that he shared with me, and I asked it, can you give me neighbor numbers for the C3 by C3 solution? And what it does is it just numbers the 9 different pairs that come from C3. In this case, it's labeling C3 with 0, 1, and 2 instead of 0 up to 8, or 1 up to 9, which would be C9, the mod9 arithmetic. And so that's what I show in the second solution here. That is, in fact, the other way to do it, to consistently label the four-dimensional Rodin torus. You can see that they split up into two different groups, one where you switch both of the elements, this one, and the other one where you switch one of the elements, this one and this one. So I don't know, I think that's interesting that there's two and that's the other one. But anyway, so let's talk a little bit more about this lattice. Some of you may be wondering where this lattice actually came from. There are different ways to construct it. You could say, I want to have the cells spaced out so that every square that you go around, like this 3 by 3 square, if you add up all the numbers and they are divided, they produce 0 when divided mod9, then that's if that's a correct criterion you can use to construct this thing, except for trivial solutions. But if you're going to use all 9 numbers, then you have to do that.
Tony, could I interrupt for just 1 second?
Yes, Greg.
Okay, with these 3 charts, the charts in red,
Yeah.
I would like to suggest that the middle chart be flipped around 180 degrees so that the 7 is in the upper left corner. Then it would be more consistent. So the 7 is -2. 1, 4, and -2 are the triplet, not 1, 4, and 2. Not a huge deal, but then the 6 and the 3 would be flipped over. Does that make sense? That it would be more consistent. Then when I say consistent, what I mean is that the 1, you cycle the 1, 4, 2, 1, 4, 7 around, and you cycle the 2, 5, 8 around, and you get all 3 maps that way consistently. Not a big deal, but I just
you could do that, yeah. I think what I did was the consistency criterion I applied, which is just basically arbitrary, is I wanted the top row to be increasing and the bottom row to be decreasing, and that actually flips the middle row around there, which is not terribly satisfying, but that's what I did. So anyway, these 3 things are slices of toast. They're X, T, Y, T, and Z, T. And so instead of talking about I've got to get this. I'm not completely used to using this program, so I've got to get my muscle memory trained here. I just put together a bunch of pictures. I stole them out of other people's presentations. I can go through each of these things if you want me to, but there are many, many presentations on this stuff on the Rodin torus. People who are interested in it can go and find out all of the details about it easily online in Marko's presentations and other people's, and various PDF files are floating around that describe all these things like nexus keys and the periodicities and the doubling circuits and all that kind of stuff. So I don't want to spend too long on that. You'll just have to take it as given if you haven't gone into this stuff before. And if you haven't, just imagine that what we're doing is, instead of thinking about everything happening on this two-dimensional surface, which is curved, we're now going to think about everything happening on a four-dimensional space, which is not curved. It could be curved later, but we're just thinking of it as a big four-dimensional block, which is a tesseract, what they call a tesseract. And so, yeah, I just showed those pictures because if you're not familiar with the Rodin lattices, it helps you to see pictures of these kind of things. And that is it for the first part of the talk. And what I want to do now is show you some things which Ruadhan has made, which are pictures of these things. And here, what I can do, I don't know if Ruadhan wants to explain this. Actually, Ruadhan, do you want to talk about these things? I bet get Ruadhan mic'd up so that he can interrupt, because he's supposed to be jumping in and keeping me straight. I'll just show you one that he produced these things in a couple of days while entertaining his wife's parents. And the reason he can do that is he just fires off a prompt to Claude Code and says what he wants, and Claude Code produces this kind of stuff. So this is a
John's going to add him into the chat, into the
yeah, get
meeting.
Ruadhan in here. Ruadhan has to be able to interrupt at any moment and say relevant things that I'm forgetting to say.
Okay, he's going to come in any second. We'll add him in.
Right. Here is this is a three-dimensional slice through a four-dimensional Rodin torus, right? And so these different colors are all the different numbers you can have. You can see that we've got black is 0 and dark blue is 8, and there's a bunch in between. I'm glad the colors are named because I'm colorblind. So if you imagine this, then this is a single time slice of a four-dimensional Rodin grid. And if I just do this with the mouse and move the mouse wheel one little click forward, then I get the thing evolving through time. You can see time changing in the number up here. You can take these things out and find waves happening. So, for example, let's turn them all off. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all gone. And then there's
Tony, would you ask
𝗏𝗏
to turn on his camera, please? Here he comes.
How can I ask him? You want me to email him? So you have here we're looking at 4 and 0, and as you move backward and forward in time, you can see that there are kind of like these traveling waves. We can make the thing bigger by there you go. There's a four-dimensional Rodin torus evolving in time. Thank you, Ruadhan, for doing this. Amazing. 4 and 3 is another interesting one. These are supposed to be waves moving in X, Y, and Z directions. I'm not entirely sure that I can see that from this. It's because it's a little jerky. There definitely seems to be some kind of motion. They're grouped, they're moving. We also look at 4 and 6. Take off 3. Well, that looks like it's moving in and out of the screen, definitely. Let's move it
Zoom
sideways.
audience on Zoom doesn't get to see Rowan, but it is here, but not on mine. No solution. Is your audience, all your chat room people seeing Rowan?
This is what they should be seeing.
Not me.
Yeah, there you can see a moving wave structure.
Because of your view, you're just gonna change your view. No.
No, oh, that view. I tried that.
Let's
Maybe
turn
did it,
those off.
and it did it.
4,
and it
7.
still didn't show.
Look at one of the usual suspects, 3, 0, and 6. So this is the
I don't know.
Marko's
I think it might
map
be because of
space.
the phone that you're on. I don't know. I can't-
Ask them in the chat room if they can see him. Can you chat with the chat room?
Yeah,
Ask them if
you
they
can
can see.
chat with the chat room too.
I don't know how.
So there's a three-dimensional cube of 369s evolving in time. As you can see, they form these linear slices.
Can anybody hear me?
Yes, Ruin.
Okay, it worked. Fantastic. We
Good.
just overcame severe technical challenges there. Thank you to everybody else who solved it on the other end.
Ruin, can you start saying intelligent things about this?
This thing here, yes. Well, not exactly. I mean, to be honest, I don't understand perfectly myself. It is.
This is 369, by the way. You've got plane waves.
This is,
of
yeah. 369. This is, yeah, plane waves of 369. This is, I guess, yeah, this is essentially part of the Rodin number map. So, and it's what's happening now is it's scrolling, it's moving through time as Tony clicks it forwards and backwards. But what's happening is you're seeing how I guess what's called the energy components rather than the material components of the Rodin number map change over time. So these are the things that they kind of they behave like solutions to the what are these equations called? The what are they called?
I mean, the equations that we proved.
The equations that we proved. I don't know if we've actually got a name for them, but they're basically they behave masslessly. Okay, the normal the full solution behaves according to the Klein-Gordon equation, which behaves like a massive particle, but this describes a massless component of it. It's a part in which the mass is 0, and this is essentially behaves more like radiation than like a massive particle that moves with a finite speed. Even though in this system there's no real speed, there's no real distance. Everything is so compactly represented that there is no real large extension of space. But maybe what I could possibly do to make what's happening, what that pattern is, a little bit more comprehensible. I could share my screen, or possibly Tony, you could go back to the number map.
This one.
Yes, exactly. Yeah. So if you press L, and if you press Shift T, and if you press X. Okay, perfect.
It's an XT.
Yeah, so this is the XT linear map. So this is not the Rodin number map. This is the Rodin number map without parity. What this has, if you look at the top line, is it just goes across 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. It's just moving to the right and from any cell in this map. It just increases the value of the number in that map by 1. And if you go down, then I believe it increases it by 1. So if you go from 1, it goes to 4, and then from 4 to 7, and then from 7 to 10, which is 1. So if going down in this map is like adding 3 to the number, and going across is like adding 1 to the number. And that's that map. It's just that simple. It's just add 1 if you go across and add 3 if you go down. That's how simple it is. Now, if you press the OR button, Right. What that did was it took every second cell and flipped it. So originally, so maybe it might even make sense to go back to L so that people can look at what's happening in the cell. There's a cell there at the top right, just to the right of the 0, 0 cell. It says 1 inside that cell. If you can see that cell, does that make sense? There's a cell with a 1 in it, and it's in between 0 and 2 at the top. Sorry, the top left of the map here. Yeah, exactly that. So if you press R, that 1 will change to an 8. Okay, but the numbers on either side of it didn't change. And the number, yeah, if you go over a little bit over to the 3, that's just past there, and then do it, that will change to a 6. If you press R. Okay, and then if you go back and then move again, you'll see that a 5 changes. The 5 changes to a 4. So
Right,
what's happening is
we're doing Greg's negation.
exactly, yes, that's what's happening. Yes, so 2 changes to do, and 7 changes to Devon, and 5 changes to dive,
Devon.
and Devon, yes.
Devon, that's a new one.
I know. So I think it's part of his system. I think Greg would agree that is completely sensible within his system. But anyway, what we're looking at here is changing from these functions L to R. What it does is it takes every second cell, like a checkerboard pattern, inside the number grid, and it flips those cells. It flips it from from 1 to 8, or from 2 to 7, or from 4 to 5, or 3 to 6. So basically that's it. I mean, that's how simple the number map is. The number map is basically it's just this linear map, where you going in one direction increases by 1, or going in a different direction increases by 3 or by 2, and then you just add in this flipping at every second step. This parity operator, and
which brings us to your formula.
Exactly. Yes, that was how you. It was you who showed me that this satisfied the Klein-Gordon equation, and I was like, oh, I better study. I better understand what's going on. And then
no, your memory's gone, Rowan.
Is it gone? What happened?
You had the whole formula for the 4-dimensional thing worked out, and
really?
I coded it up in MATLAB and started shifting the maps around and subtracting one from another. And that's how I discovered the Klein-Gordon, and that's what set us off. So, okay, but you found the space. You found the fact that the 3 Rodin toruses, the 3 possible solutions to a 2D Rodin grid, could be combined together to make a 4D Rodin grid, which was unique.
Yeah, it's true. Yeah,
that's what you discovered. That was the first thing you discovered.
But I only did any of this because after I showed you the number map, when I said, look, this isn't this interesting, you went away and came back and told me, oh, it's even more interesting. And then that was what set me on to try to find the... No, it was also, I think, maybe possibly reading Greg Vogt's paper, because I think he had a paper about lattices and the ways to label them, and or tori and ways to label them. And I basically was inspired by that to try to search for the solution. But here, this is the thing, is that this allows you to see how the number map is created. It's very, very simple. The structure looks very complicated, especially when you look at all these patterns of numbers. But when you take away the parity part of it, you see that it's just linear increases in every direction. Whatever direction you go in, you're increasing the number of that's inside the cell by a fixed amount. So going right in this map increases it by 1, and if you do it with the Y map, it would be by 4, and with the Z map, it would be by 7. So that's it. And also, there's just in that formula that's on the screen, there's a missing plus 3t.
Oh dear. Fortunately, we can just fix that, actually. minus 3t, right?
It depends on the signature.
Okay.
But you can use. I think in the calculations that we did a long time ago, we used plus 3t.
Oh, why is my pen not working? Oh, because I'm probably on the wrong. I hate layers. I hate layers in painting programs.
Yeah, I don't know how to understand them.
Plus 3t. There you go. So what you got there is 1 times x, as Rowan said, 4 times y, which is minus 2. No, sorry, it's minus 4 is 7 times z, which is minus 2.
Yeah.
And 4 times y, and 3 times t. So the reason that we associate t with 3 is because as you move along the x, y, and z dimensions, you go through kind of a 9 or 18 cycle, depending on how you're looking at it. That just looks like kind of messy, but they called it the nexus keys. I don't know why they called it the nexus keys, but if you move in the 693-396 direction, it's a unique thing. It has its own periodic behavior that's different from the other 3 directions. So if you make this unique 4-dimensional space, and you're trying to think about it as a space-time, the natural thing is to think of the 3 spatial directions as being the nexus key directions, and the temporal direction being this direction of 396. Right, Rowan, why don't you take over from there and explain the rest of the formula with the parity?
Okay, yeah. So the parity part. So the parity part is just, so the thing is that minus 1 to the power of 2 is just 1. So when x, y, z, and t are integers, they're all whole numbers like 1 or minus 1 or 2 or minus 2 or 0. When you add them all up, you either get an odd number or an even number. And if you get an even number, then minus 1 to the power of that even number is 0. So the only effect that the parity checkboard term has in this equation is to flip the sign when x plus y plus z plus t is odd. And that happens if x plus y plus z plus t is even and you change one of them. If you change another one, then it becomes odd again. And if you change another one, it becomes even again. So it doesn't matter whether you change x, y, z, or t. Moving any one step in any one direction is going to cause a change of sign. And that's why you get this checkerboard pattern on the otherwise linear map. And that's what converts it into something that essentially satisfies the wave equations that we expect in physics. Instead of being just a straight line motion, it produces oscillation. And due to the features, I'm sorry, you may be hearing some noise created by my cat in the background, but due to the features of Mod-9 arithmetic, this is the I think what was the startling part of what I found exciting about the number map when I found it first. There is a doubling direction. There's a direction along which doing this corresponds to doubling. Moving in the t direction corresponds to going along the 1, 2, 4, 8, 7, 5, 1 cycle. And that is something that you would never expect, because that is it's exponentiation. It means in mathematics you're raising 2 to the power of 1, 2, 3, 4. You're increasing the power. You're doubling every step you go. And what you would not expect is that you could achieve this doubling effect just by moving one step at a time and flipping the sign. And that's I think the feature of Mod-9 arithmetic that you don't really see in I don't know. It's just something that allows you to encapsulate multiple things like arithmetic operations, exponential operations, geometric operations. All of these can happen within a very, very small system of numbers.
Yeah, if you're solving a differential equation in time, linear differential equation in time, you have 3 different kinds of behavior. One is exponential off to infinity. Another is exponential decay down to 0. And another one is oscillation, which is sort of halfway in between. And
Exactly, yeah.
And so here we have exponentiation going in both directions, and oscillation.
And there's
so it's a little bit
well,
like it's a little bit shouting like I am time, I am time.
It is, and that's the thing, is that the other three directions, the numbers 1, 4, and 7, they're not divisors of 9. They don't divide evenly into 9 the way that 3 does, and 6 doesn't divide evenly into 9. But if you multiply it by 3, it becomes a multiple of 9. So 3 and 6 are they're not exactly 9, but they're things that if you multiply them by 3, you get 9. And that means that they square to 0. So 3 multiplied by 3 is 0. 6 multiplied by 6 is 0. And those numbers that square to 0, they don't behave like space in this equation. They behave in a different way. And just because what Mod-9 does is it produces from those numbers these patterns of doubling, like exponential increase, exponential decrease, and oscillation, which is basically how physical fields behave in time. So it basically singles out. This is a mathematical, like a arithmetic way of singling out time from space. It separates space into it separates 4-dimensional space-time into a 3-dimensional space and a 1-dimensional time. You don't have to tell it that that space, that 4-dimensional space-time has one time dimension. It already knows. It's something that already encodes that, which is it's very striking.
Yes. So that's where we were about, I would say, the summer of 2018.
That's all right.
Right?
Yeah.
I was in Lisbon, you were in Dublin, and we were, I wasn't really taking it that seriously. But when I called you up and you told me that you had this formula, that simplified things, because then you can just go and code up the formula in your computer and start working on things. But let's see. Let's go back to the talk plan to make sure we're not getting derailed here. What have we covered? We've got up to your formula. We've explained your formula, separation of space and time. Oh yeah, physics on the grid. So the next question is, and this was, we got the idea that there was some kind of dynamics on the grid, and everything that Marko was saying in his talks was kind of like along the same lines. It was just in his language. So we were trying to translate some of his ideas into the more standard mathematical ways and physical ways of describing things like this. And so if you have a 4-dimensional thing where 3 dimensions look like space and 1 dimension looks like time, and if you're a physicist like Rowan or somebody who knows a bit of physics like me, a little bit, you're like, you want to know how you can have Minkowski space in there. How can you have, you see, in physics, time squares to -1 and space squares to 1, or else space squares to -1 and time squares to 1. And that's how you get relativity and light and all the things that we see in the universe. When you're looking out at the stars, right? All those stars are right there beside you, right? You think that they're really far away, but they're not. They're right where you are, because the distance that the light travels in going from the star to your eye is 0 in Minkowski space. So the entire sphere that surrounds your body is just a complete list, array of things that are distance 0 from you as you look, basically, in Minkowski space. You can't do that. If it was just if time, space-time was a normal 4-dimensional thing, a normal, all positive signature thing, you wouldn't have any of this. So our universe is made that way. It's not it's not something that they pulled out of a hat. It's really it's something that in some way, maybe Greg would disagree, but it's something that has this Minkowski structure. if Greg disagrees, he would have a different way of talking about the same thing that they're talking about. He would just disagree about the way of talking about it. But the phenomenon is real. And so we wanted to find some kind of equation. We've looked a little bit at those, clumpy waves that were occurring, and we want to find an equation, a physics equation on the grid. And so then we go over to my world over here, which is me working away in MATLAB. Nowadays, I would probably be using Python and Jupyter and all those things if you know about it. But back then, I was still using MATLAB. And so what you're looking at here is a hypercube, which is a 5 by 6 by 10 by 20. So it's a hypercuboid. It's not actually a cube. And each one of these grids, if you took all of those grids that is in a row like this, and you put them beside each other, you would get a cube. And if you took all those cubes and put them beside each other, you would get a hypercube or a 4-dimensional cube. And those are a whole bunch of numbers which form that 4-dimensional hypercube. And then this function over here, which is called R, X, Y, Z, T, it simply computes what Rowan has derived as the equation which describes the 4-dimensional Rodin grid. One of them anyway. But actually, there's something I probably ought to say before we do all this. Well, no, we can do that later. We'll do it later. It's about the uniqueness of the grid, because that's part of Rowan's discussion with ChatGPT, which we're going to go into, which is very interesting, actually, coming up. So then what I'm doing here is I'm taking differences in the grid. So that means, I'm taking the grid and moving it one step to the left and subtracting it from the one I had before, or I'm moving the whole thing up one, the whole 4-dimensional block up one, and subtracting it from itself, or I'm moving it all one step forward in time and subtracting it from itself. So basically moving it in the X, Y, Z, and T directions and subtracting it from itself. And that gives me another Rodin grid. Now, that's not really, you could stop there and go, well, this is not really going anywhere. We're just getting more Rodin grids by performing this difference. When I'm doing this difference, what I'm doing in discrete space is what you would do with calculus in continuous space, which is to take the derivative. The diff here, MATLAB's diff function is kind of like the, it's a discrete version of a derivative. And we're looking for the discrete version of differential equations, because we want to find something to do with waves. Waves are described by continuous differential equations, but in this discrete grid, we're going to be making these discrete differential equations, or difference equations, they're called. Now, I compute a whole bunch of them. I'm playing around with this, trying to find different ones, seeing what they look like, and slowly forming the intuition that if I do a certain number of differentiations, or a certain number of these diff operations in sequence, if I perform the right set of diff operations, I'll get back to where I started, right? Because there's only a finite number of different Rodin grids. And so if I keep performing operations on them, I'm going to be walking around in that finite space. And every now and then I'll loop back into a grid that I was at before. So you can imagine this space of different Rodin grids, all, and I'm walking around in that space, like, oh, you can see me, so I can actually use a physical, I've got a bunch of these different Rodin grids and I'm walking around from them. And if I differentiate this one, and then I differentiate it again and find myself back where I started, that would be interesting. That would be a wave equation, because that would say differentiating twice gives you back the thing that you started. So then you'd be saying, d2r by dx squared equals r, because if I differentiate it twice and I get back where I started, I would get d r being the Rodin lattice I would get a differential equation, second order difference equation, d2r by dx squared equals r. That's not actually true. Nor is it true that d2r by dt squared equals r. None of those things are true, but what actually is true, I'm just going to read it out. d2r by dt squared minus d2r by dx squared minus d2r by dz squared minus d2r by dy squared equals r. And that is the equation that is satisfied by these numbers. And that's called the Klein-Gordon equation. It's like a wave equation. You know, if you have a wave equation in, throw a stone into the pond and the ripples spread out without any, they just keep going forever, they don't die down. That equation of that is d2r by dx squared plus d2r by dy squared equals 0. I hope I got that right, Ruadhan.
It's actually minus, but yeah.
Oh, minus, okay, so it's the, and there's a time in there, of course, as well.
Yeah,
so
you started to t, yeah.
Yeah, so it's x, y, so that's a wave equation, x, y, and time for, x, y, and t for the ripples on a pond. And here we find one with x, y, t, and z for waves moving in the Rodin lattice. And it's the same as the what they call the Klein-Gordon equation. Now we can go and look at the Klein-Gordon equation in Wikipedia, which is also an interesting thing to do. And this is what, now I'm in Janet's house. I'm like, I've discovered that it satisfies this relationship. And I know that that relationship is something to do with quantum theory, and that's about it. And I'm sitting in Janet's house. I'm looking the thing up in Wikipedia, probably reading exactly the same things as you see here. Klein-Gordon equation is a relativistic wave equation related to the Schrödinger equation that you've all heard of. It is a second order in space and time and manifestly covariant, Lorentz covariant. It's a differential equation version of the relativistic energy momentum relation. So when you're talking about space-time, as they were when they were trying to do build some kind of version of quantum theory that worked in this Einsteinian Minkowski space, the thing they were concerned to get is Lorentz covariance, which means that basically in relativity, in three-dimensional space, you can rotate the space in all the three axes, x, y, and z, and you get the same physics. It doesn't change it, right? But if you go to space-time, you have this extra thing where time is behaving differently from space. And so you get rotations not just in space, but rotations in space-time as well. And they're not really rotations when you go to space-time. It doesn't move you in a circle. It moves you in hyperbolic, what they call hyperbolic trajectories. But anyway, let's just call them all rotations. And what Lorentz covariance means is just the same thing, that as you change the coordinate system in space-time, you don't change the physics. And that's the fundamental insight of Einstein's theory of special relativity, which is just for things flying around in velocities at space-time. But when you do, when you want to do quantum mechanics and particle physics and have energies and stuff like that in space-time, then you've got to take what they would call non-relativistic energy theory, and you've got to turn it into relativistic energy theory. And that's what this equation is, the energy momentum relationship. And when you differentiate that thing, you get this Klein-Gordon equation. So the Klein-Gordon equation is really bringing together two very interesting things. It has got Einstein and Lorentz and Minkowski relativistic space built into it. And it has not just that, but it has the energy conservation relationships that you would be using in quantum mechanics. built into it. And that is why it is the fundamental mother equation of what they would call relativistic quantum theory. It's got the relativity in it, it's got the energies in it, you know, the momentum of the particles, and it's got, you know, mc squared, Einstein's m. This is basically E equals mc squared with some extra stuff stuck in there. It's basically that. It's Ruadhan, you would say all this a lot better, I'm sure. Do you want to, or did I do okay?
I guess what I can say is that there's the E equals mc squared is only true when a particle is at rest. That's the amount of energy that a particle has if it has no kinetic energy, the amount of energy that comes purely from its mass. And in the equation here, the relativistic energy momentum equation, it explains what fraction of its energy comes not just from its mass, but also from its motion. So it has a momentum p in that equation.
That's
and
right.
if p is 0, that
Then
just
it's
becomes E equals mc squared.
Right.
But
And then,
if p is non-zero, if it's moving, then it's got kinetic energy as well as energy from its mass, and that contributes to the total energy. And they add up basically like in the Pythagorean fashion, like you know, the sides of an orthogonal triangle.
right. And so I'm basically just differentiating this thing twice with respect to space and time coordinates, and that gives me the Klein-Gordon.
Yeah, what you do is you just replace E with d over dt, and you replace p with d over dx. So the momentum becomes a gradient in the spatial direction, and E becomes the rate of change.
Good. Yes, that's right. I knew that. All right. So we've got the Klein-Gordon. Maybe we should go now to let's see where we are on the schedule. Yeah, this is the equation for, I said this already, but I'll say it again, the equation for bosons, which are the force carriers. We discovered it numerically using the MATLAB grids that I showed you and that code, and then we proved it using formula. So at this point, I think I want to go to the mother of all information sources. You know what that is?
I don't know. What is it?
It's Ruadhan. No.
No,
you know, actually, I used to talk to Ruadhan all the time, but then AI came along, and
you don't need me anymore. I'm fired now.
But Ruadhan talking to AI, there's something. So we're going to do another one of you talking to AI. Ruadhan goes, consider the function which we've been talking about. Prove that R satisfies the Klein-Gordon equation appropriately converted for discrete time and Mod-9 arithmetic. You know, that's a very succinct prompt. You know, you've learned how to prompt pretty well, Ruadhan.
Yeah, well, I don't want to feed it the answers. I don't want it to be like pleasing me. I want to probe it and see if you just give it the minimum and tell me if it's going to see the things that I see.
Yeah, I mean, and it's right there. I mean, look at this. If there are any AI skeptics in the room, you know, because AI can't count the number of R's in strawberry or something, let me just tell you that people are doing technical work. We are more or less, if we've tried it on our problems, we are more or less blown away by the emerging capabilities. Incredible, sure, right, Ruadhan?
Absolutely, so yeah. I mean, yeah.
So you know, it had to think for 4.5 minutes, but it's gonna go in, and it's just going to go cranking through this, knowing exactly what you mean. Why am I not able to? Okay, we'll just do it with a scroll wheel. Is the text big enough for everybody, or shall I do that thing?
It's a little bit small on my screen.
Okay, let's just crank it up a wee bit so everybody can see what's going on. There's the equation we've been talking about, so I don't have to make a slide with it on. And we're going to work on the unit hypercubic lattice that of four integers. Integers in 4-dimensional space, and use the standard central difference discretization of the Klein-Gordon operator. So this will be the Klein-Gordon equation. That box thing is that sum of double derivatives that we've been reciting. It's called the D'Alembertian, after some French mathematician, and it looks like that. It's a gradient in time minus the gradient in space in the three spatial directions. And we're going to look at the R, which is the field that Rowan has defined, which is the Marko Rodin four-dimensional space-time. And then we're going to take that delta in, there's delta because it's discrete, otherwise it would maybe be an upside down triangle. But here's the delta in some direction, epsilon, which is epsilon is just x, y, z, or t. And there it is. If you're doing these are essentially curvatures. If you're doing a curvature along an axis, what you do is you take the middle thing, double it, and you take the one to the left and the one to the right, and you add it. And that gives you the discrete time analog of a curvature. It's just the difference between two gradients. So if you had 1, 2, and 3, and you took 2 minus 1 minus 3 minus 2, you would get 1 plus 3 minus 2, basically. So that's a discrete curvature along a direction in the Rodin space-time. And then ChatGPT goes off and proves a little lemma, which is very handy, which is if you take that gradient, just take the gradient of the Rodin in one of these directions, it turns into -4 times the Rodin map. I didn't know that. I didn't spot that. But
I actually remember both of us proving that. Or at least I proved it, and I think I sent it to you when you asked me to give me a symbolic proof. You figured out that this was true, and you said give me a symbolic proof, and I think I proved that lemma.
It's true. Actually, I don't really remember which things I did and which things I didn't do. So I probably found that and made you prove it. But in my memory, you found it. But you know.
No, you found it definitely, and said you sent me an email saying prove this, and I thought you already had a proof. I thought you were just challenging me to find a proof that you'd already found, but in fact you hadn't. You just realized it was true, and you just wanted somebody else to find the proof.
Yeah, you know. It was a dynamical system in which Rodin is the math wizard, and I'm kind of like, you know, basically flailing around looking for things.
But you're the one who found the things. But yeah,
flailing can work though. So there we go. We get out of this the discrete D'Alembertian on R. We do it twice. Here he does it twice. Discovers that the D'Alembertian, the curvature operator, summed up is 8R. Well, you could stop there and go, no, that's terrible. That's nothing like the Klein-Gordon equation. Except, of course, 8 is -1, right? In Rodin math and Rodin and Greg Volk math. So that turns into the D'Alembertian of R is equal to -R, and that's the Klein-Gordon equation. And if they had come out and said the D'Alembertian of R is equal to 7R, which it might do in some other base, right? I don't know. I haven't checked. That wouldn't be the Klein-Gordon equation. So, so it's not trivial. I mean, the fact that the Klein-Gordon equation comes out is probably a feature of the Mod-9 space, and probably isn't a feature of other spaces. Rowan, what do you say about that?
Yeah, it's well, what I'd say is that you can do the same thing, I think, in higher dimensional spaces. Like in a 5-dimensional space, you can do it with Mod-25 instead of Mod-9. But the problem then is you get 2 time dimensions. So if you have Mod-9, the 6 3-dimension is the only time dimension. But if you have Mod-25, then there's a 520 dimension, because 20 plus 5 is 25. So those are 5 and 20 are opposite numbers. So that there's a 520 dimension that you can move it. And there's also a 10-15 dimension. And both of those, all 4 of those numbers, 5, 10, 15, and 20, if you multiply them by themselves, you get 0. So those are all time dimensions. So this is what's special. I mean, I think that Greg is writing a whole paper. There are other reasons why 9 is special. But at least from the point of view of physical reality, what we don't want is a physical theory with 2 time dimensions, because if there are 2 time dimensions, then that means that you can go in a circle in time. You can always be moving in time, and you can get back to where you started. and that would mean that you could cause a paradox. You could kill your grandmother before you were born, and so on. So, so that's why it's basically considered unrealistic to have more than 2 time dimensions. That's why Mod-9 is the only one of these systems that seems to describe physically sensible space.
Well, I'm sure they regard our universe as unrealistic.
Well, if people live in, I mean, we could, yeah, I don't know. We could speculate about higher beings who can live in dimensions with 2 time, or in spaces with 2 time dimensions, and know how to navigate it without causing paradoxes. But it's it's too mind bending. It's far more mind bending than this.
It's very interesting, though. You know, those higher prime spaces that Marko always talks about with their, you know, it's very interesting to speculate and think about those things.
Peace, we're in
What's that?
Sedona. We're in Sedona here. Please talk about multiple time dimensions and blow the mind. Let's go.
All right, Ruadhan, talk about multiple time dimensions.
Yes.
Okay, what I can say is that I think if you use 3, then you get 1 time dimension, like 3 squared, meaning 9 is the modulus. You get 1 time dimension. If you use 5, you get 2 time dimensions. If you use also you get you get 2 time dimensions. I think if you use 7, then you get 3. You get more and more. You get twice as many time dimensions for every 2 that you add on to the dimension of the prime that you're using. You know, whose square is the modulus. You get an extra time dimension. So you keep getting more and more time dimensions, and that's yeah, that's well, I don't know. From a physicist's point of view, that's not good. I'm just thinking to myself,
Retreat.
There are too many paradoxes here. We can't cope with that many possibilities of paradox. Let's retreat back into something safer. So
let's say it's kind of like one of those timey-wimey things, right?
Yeah, it's a timey-wimey thing. You need extra structure. If you're going to have 2 time dimensions, you need something to stop you from killing your grandmother.
Right. Timey-wimey, I'm sure you know that is a quote from a Doctor Who episode.
Yeah, I remember it, Doctor. Wibbly wobbly timey-wimey.
That's right. All right, so there we go. We are looking at the Klein-Gordon equation in the Rodin lattice. Now, Ruadhan, I think you told me that the Klein-Gordon equation is in 4 dimensions is only satisfied by the Rodin number map. Is that right?
No, it's not actually right. And what it shows, what's on the screen right now shows you exactly the thing. What it says is that any linear form, essentially of this form, it doesn't need those specific coefficients.
Oh yes, you're right. You're right. Oh right, of course I remember now. This comes later. This comes further down, right? That's right.
Yeah,
the result holds for. Oh yeah, here we go. Actually, it's right here. I don't know why I'm asking you. The specific coefficients 1, 4, 7, and 3 that we put into the linear part of the R function, they never enter the lemmas. The lemmas for R outcomes, they cancel. So the result holds for any linear form with alpha x, alpha y, alpha z, and alpha t. Different but standard symmetric discretizations of the D'Alembertian only rescale a constant prefactor and the required m squared, because there's a mass in here. The mass for our simple system is 1, but in the Klein-Gordon equation, you would have the particle would have a mass m, and the photon, for example, would have a mass of 0. Light is massless, and the required m would adjust accordingly. Here, the central difference choice yields the neat condition of the mass being 1. So you're pushing back on ChatGPT and telling it that the result may hold for any linear form, but requiring different spatial dimensions to be inequivalent, and adopting canonical choices leads to R. And you can just spit that out, and ChatGPT knows what you mean by inequivalent and canonical choices, which is amazing.
It does, yeah.
And off it goes. 19 seconds is all it took for this one. So let's read this. Don't know if we want to go through every sentence, but we definitely don't want to miss any important points here.
Yeah, but I think maybe what's good about this answer is maybe point 3. I didn't have to tell it this. it already understood that time should be inequivalent to space, and it figured out that's why 3 has to be associated with t and not with x, y, or z. X, y, or z have to be different to t. And it also figured out that, yeah, 1, 4, and 7 are the numbers that should be associated with x, y, and t.
Right.
So, yeah.
Yeah, so in 3 and 4, it's picking out the canonical directions as being made from 1, 4, and 7 for space.
Yeah.
Shear 1, 4, and 7, and 3 for time.
Yeah, and I didn't have to tell it that. I just told it, like, do whatever's canonical, meaning do whatever is, you know, what a mathematician would do if they were bringing it to its tidiest form.
Right. If anybody wants to slow down the scrolling and ask questions about any of these points, just go ahead. Otherwise, we might skip over some of them. Oh, this might be important to say that when we say unique, we're saying unique up to what they call a coordinate permutation, which is kind of like swapping the x-axis with the y-axis, or making the x-axis minus x-axis instead. So those are things we don't consider those to be really different solutions. They are equivalent up to trivial permutations.
Absolutely. And somebody called Zoom user just said that the answer to the time dimension could always be found as half the number of circuits. So I think that means that the answer to the time dimensions, it may mean that the number of spatial dimensions that you have, half the number of circuits. Okay, I'm trying to understand. What I would think naively was that it meant half of the number. If you take the you have 6 steps in the time dimension. If you take half of that, then you get 3, and that would be the number of spatial dimensions. Or you can subtract 1 from the prime and half it. If you subtract 1, if the prime is 3 and you subtract 1 from it and half it, then you get 1, which is the number of time dimensions in 3 dimensions. So I think that checks out.
Okay. So yeah, it's picking out this canonical set. The natural step size distinguished by the modulus 9 is in fact 1, 4, 7, and 3. All the things that Marko spotted, years ago.
Oh, it's Randy. Okay, this is great. Good to know that this is. It just said Zoom user.
So, for example, we could have 2, 5, 8, and 6, right? That would work. That would also give a Rodin map. Would just be shifting the numbers around a little bit, but the time is always going to be 3 or 6, and these guys are always going to be like a particular triplet of the remaining numbers, which are separated by 3, and that gives you all the different Rodin lattices in 4 dimensions.
Yeah. So here I gave it a pretty long. This is actually something I copied and pasted from an email that I'd sent.
Yeah, this is
just summarizing.
This is where I don't think we're going to run for 4 hours because we've actually gone through most of the stuff. But this next bit is the hard part.
Right? It's the geometric algebra part. Yeah, it's
yeah, that's what I have to explain the mathematics that most people don't know. So I remember earlier on I talked about the Klein-Gordon equation having a square root. Some equations have a square root. Maybe I'll show it over here. This is my Mathematica simulator of what we call Clifford algebras, and the Clifford algebra is called CL. And you give it a number, 1, 3, and 0. 1 means the number of things that square to -1. 3 means the number, 1 means the number of things that square, number of basis vectors. If you have you got a vector space, some axes, one way of talking about the point x, y, right, is to say that it is x times E1 plus y times E2. Where E1 and E2 are unit vectors in those directions. In fact, we could I've made a unit vector for you here. I've made a unit vector in 4 dimensions, and it's called D1 times E1 plus D2 times E2. So these D's are the coefficients, and these E's are the unit vectors. And so this is we're in 1-3 signature. E1 is going to square to E1, E2, and E3 are going to square to -1, and E4 is going to square to 1. So 4 is the time dimension, 1, 2, and 3 are the X, Y, and Z dimensions. And I'm going to take a vector in that space, and I'm going to do what you cannot do. Well, you can do it in this case because it just reduces to the dot product anyway, right? Dot product and what they call the geometric product are the same thing in this case, but in general they're not. In general, with this one you can get things called bivectors as well. A bivector would be something like, actually I'll just show you the whole thing. Why don't I make I'm going to make a whole big where is that percentage? That's there. This is my notation for a complete multivector in this 4-dimensional space. We got a scalar, we got a vector, which should be letting me select part of it, right? It should be letting me select part of it. It's not. Okay. E1 through E4 is the vector. E12, E13, E14 up to E34. There's 6 of those terms. That's called a bivector. It's a bit like a plane. If you took two vectors and took their geometric product, usually multiplying vectors gives you the dot product, gives you a scalar, which is what we've got up here. But otherwise, in the geometric product, you actually get a bivector as well. So if I was to say, A sub 1, what are you saying something, Ruadhan?
I was going to say that just for the sake of clarity, where it says E12 there, it's got an E and a little 1 and a little 2 beside it. That means E1 multiplied by E2. That's right. That means it's the vector E1. So E1, E2, E3, and E4 are vectors. They point in different directions. And the object called E12 is the product of 2 vectors. It's like an oriented area. It's like if you take a horizontal vector and you multiply it by a vertical vector, you could take a horizontal arrow and imagine sliding it along a vertical arrow, and it would carve out a 2-dimensional area. So that's what E12 corresponds to, and E13 is the same thing with E1 multiplied by E3. So the subscripts tell you what things need to be multiplied to that object.
So yeah, so out of vectors you can make these planes, and if you multiply a plane by another vector, you can get a volume, and you multiply that volume by another vector, you can get a what they would call I suppose a 4-plane. And depending on your dimension, you can keep describing these linear subspaces using this kind of stuff. And it's a very useful language for reformulating physics. It's very beautiful mathematical formalism, actually. And the reason it's so much richer than vector matrix algebra that you might know about is shown here. If I was just to take the dot product of these two things, A dot B, I only get that scalar term, right? But if I take what's called the wedge product of these two things, like that, I get this other term here, which is the rest of what they call the geometric product, and that's the planes. It has coefficients that look like this. Each one of them is a little sum of products, but they're just numbers, right? So just like a line can be, a vector can be given by A times E1 plus B times E2. So you can just write a plane as A times E12 times B times E13, all the way up to E34. And you get a plane, basically. And so you can describe all these things, and you can just find intersections between them. You can make bigger spaces by combining them with this wedge product. You can do projective geometry. This third number here is actually how many things square to 0 in this thing. So if you have one of those things that squares to 0, you can do what's called homogeneous coordinates. It's a projective geometry, which is actually underused language for physics. But anyway, this is just a little short tutorial on what Clifford algebras are about. It's very hard to pick this stuff up in one go. I'm just trying to give you the intuitions. It takes, because it's not something that you're really taught in school, it actually takes years of study, and it's very helpful to have a program like this to use if you want to study this language. I wrote this one myself. It's about 100 pages of Mathematica code, and it probably took me 6 months to write. And probably now you could get the thing turned into a web app in about 5 minutes using Claude.
Yeah, I'm afraid so.
In fact, I nearly did that last week. It was actually slightly annoying. It was actually annoying me that it was working. You know, it's like, you know, what is it, John Henry and the steam hammer? You're like, all right, I'll use the end of my strength to try to prove these theorems, but after that, it's all just going to be automation.
Mm-hmm.
You know? But anyway, here we have a scalar. So imagine these d's, instead of being coefficients of a vector, right? Imagine that they were derivative operators. And you can do this kind of thing. Just pretend that this d, instead of being a number, is in fact something which is doing these diffs. So when I say d1, e1, what I really mean is d by dx. When I say d2, e2, what I really mean is d by dy, and d3, e3 is d by dz, and d4, e4 is d by dt. So, so this thing here is exactly this gradient thing that we've been talking about in the discussion here. These gradients, these things here are exactly these d things. And now we're going to look at not this double derivative thing. We want to take like the square root of this differentiation vector. So instead of this double derivative thing that we've made, we want to find this thing here. We want to find this thing here. This is what Dirac did to get from the Klein-Gordon equation to the equation that will that bore his name. He factored the Klein-Gordon equation into two things, right? So here what you can see, as I multiply this this is now a derivative operator d. If I multiply it by itself, I get this squared derivatives, and this is exactly this D'Alembert thing we've been talking about, where we differentiate you know, now that I'm looking at this, it appears to me that 2, 3, and 4 are the spatial directions, and 1 is the time direction. Yeah. Yeah. Be. Has to be. Yeah. Okay.
Yeah. Yeah. It's the only way it could be.
2, 3, and 4 are negative signature, and time is positive signature. That's what we've got. Yeah, it's gone like that. I played with the order of these things, so this might be an old version of the program. But anyway, this is exactly this derivative operator that we've been using in the Klein-Gordon equation, this squared D'Alembertian thing. This is this box thing that we've been looking at, this box R, this is the box. Now, what Dirac did is he tried to go in and find a way to write the this thing here as a product of two of these things, right? And actually, probably we should I should have had that already typed up to show you, but we can look at it in Rowan's in Rowan's next question to ChatGPT. You know, Rowan, sometimes you explain to ChatGPT's things that you don't have to.
Yeah, I know. Well, actually, I copied and pasted that from an email that was waffling on a lot of different topics.
Oh,
this is the part I selected.
Oh,
I just copied it. I didn't actually.
Right.
I didn't write that for ChatGPT. I wrote that in 2019.
Right, that was your email to 𝘗𝘳𝗀. Okay.
Exactly. Yeah.
Right. Okay. Well, do you want to take it from? Do you want to take it from here? Because I think you're really better qualified to talk about the.
Okay, I may need you to scroll up and down. I don't have my screen shared, but
yes.
Yeah, so maybe, yeah, if we can go up, what we can see is that as Tony was saying, this Klein-Gordon equation here, it's the way it's written here is that the second derivative in time, which is d squared divided by dt squared, minus the second derivative in the x direction, minus the second derivative in the y direction, minus the second derivative in the t direction, plus 1, that if you take that whole operator and apply it to psi, that you get 0. That's the Klein-Gordon equation. And what I suppose the insight of Dirac is that this Klein-Gordon equation can be factorized. This says something multiplied by psi is equal to 0. Or if we were to rearrange it a little bit of a different way, it would mean that this thing here, the D'Alembert multiplied by psi is equal to minus psi. So it means, applying this second differential operator, like asking, what's the, if you take the second derivatives of this thing in every direction and add them up, but with time having a different direction, then what it does is it changes the sign of this function. It basically multiplies it by -1. What Dirac observed was that you can factorize this. So this is like doing this thing, multiplies it by -1, but we can separate it into doing the same thing twice, applying the same operator twice. And then what we can do is we can say, well, if applying this second operator twice multiplies it by -1, then maybe multiplying it by, maybe using this operator once multiplies it by I. And that's what the Dirac equation is, essentially. It says that instead of saying, we differentiate twice and we get a factor of -1, it says we differentiate once and we get a factor of I. And so that's essentially what the Dirac equation is. But what the Dirac equation needs is it needs an algebra where things don't commute, meaning AB multiplied by BA is not the same as, AB is not the same as BA, essentially. Multiplying the order in which you multiply things makes a difference. So what Dirac did was he used complex 4x4 complex matrices to construct these objects that behave this way, where AB is equal to minus BA. But inside Clifford algebra, the objects naturally behave that way. So these objects that Tony was calling E1 and E2, these are unit vectors. In Clifford algebra, E1 multiplied by E2 is equal to minus E2 multiplied by E1. So you could think of it kind of geometrically as if you have, imagine you have two arrows. One is a vertical arrow, one is a horizontal arrow. You can slide the horizontal arrow up along the vertical arrow and it carves out a space. And if you do that, then you get a parallelogram. But the other thing you can do is you can slide it the other way around. You can slide the vertical arrow along the horizontal arrow, and that carves out the same area, but with a different orientation. You have the sense of circulating around that parallelogram is the opposite to the sense that you would get if you slid them the other way around. So essentially, this is the anti-symmetric feature of essentially Clifford algebra multiplication. Vector multiplication has the property that if you multiply, A by B, you get the same thing as minus multiplying B by A. So those are the things that became the coefficients in the Dirac equation. So they're called epsilon mu, is it? Oh no, where do we have the Dirac? Is there a definition of the Dirac equation inside the answer that we could scroll to?
Where?
Dirac...
I'm caught between this, which is a little difficult to read.
Yeah, my text is probably too hard to. It doesn't have the formatting.
And what ChatGPT spits out, which is very pleasant, but we'd have to find the right bit. Here we are at the end.
Yeah, there it is. There, it's the D. That's right. So in the thing that I copied and pasted to it, I missed that in a factor of 2, and this is the pro version of ChatGPT, so it figured out that I missed a version of 2 and put it back in and fixed it. But it's this D tilde operator, and does it have a definition of the D operator somewhere? Maybe somewhere above that.
Well, it's got that d squared is equal to half the D'Alembert, right? That's here.
Okay. Okay. It must have defined d before it figured that out. There it is. So that's d.
Right.
So d.
Yeah,
there you go. Yeah. So d is okay from 0 to 3.
A sum of basis vectors times derivatives, exactly what I was showing
Exactly.
on the Mathematica screen. These were the d's and these are the e's.
Yeah. So the e's there are vectors, and the deltas are differential operators. They're
like
different
saying,
operators.
It's a bit like saying what is the difference when I go in this direction, right?
Exactly.
You could actually go in any direction.
Yeah. What this does, it tells you how fast the function changes when you go in any direction. Right. That's essentially what the Dirac operator does. But if you square it, then yes, you get a quarter of the D'Alembert.
Right. So that's basically, so these equations here are basically what I was showing on the Mathematica screen, except the quarter was missing.
Yeah, I missed that out as well. It was just a brain fart, I guess.
I was squaring d and getting the I was squaring the d here, this thing here, and getting the D'Alembert, the thing where the differential operator that's in the Klein-Gordon equation.
Right.
So then the trick is to find a relationship with R, the Rodin lattice, which involves this d, right?
Yes, and you figured that out, or at least you found the 𝗧 paper, I believe, that produced the solution to that.
I think I was throwing things at you. That doesn't necessarily mean I figured them out. I knew what to throw at you. Is it? I feel like we're in our own little world. Are people still there?
I don't know. Maybe nobody's listening. But yeah, I think if we scroll down a little bit, does the part about the 𝗧? It may even mention 𝗧 in the
well, up to here, look, Rowan, up to here, we're really only recapitulating what we've already done with the Klein-Gordon. But here's where the Dirac factorization mod-9
This is exactly, that's the part, yeah.
So this is what
psi equals 𝜳j, yeah.
This is the hard part. Now you have to explain this bit.
Okay. So if we look at this equation here in the middle of the screen, it talks about the lattice Dirac equation, and it basically says you differentiate psi, and you get psi multiplied by g, where g squared is equal to -1. Okay, now this is going to take some Clifford algebra to explain what is meant by g, but this is in the original Klein-Gordon equation. There was a second differentiation, and it multiplied by -1. And what this Dirac equation here is saying is you do a single differentiation, and it multiplies it by g, where g is a square root of -1. So this is like essentially the square root of the Klein-Gordon equation. It's saying, if doing it twice multiplies it by -1, then maybe doing it once multiplies it by 1. So that's the Dirac equation. And this is the construction that's underneath this, basically d tilde or plus or g, that is a formula that will take a solution from to the Klein-Gordon equation. If or is a solution to the Klein-Gordon equation, then dr plus or g is going to be a solution to the Dirac equation. And that was proved by 𝗧. I think it's actually a short proof of that given up above, but I don't know if people actually need to see the proof.
He didn't prove anything to do with the Rodin lattice, but you used that method to produce the Dirac in the Rodin lattice. So if you've got an R, which is a 4-dimensional Rodin lattice, and you do this d tilde operation, which is just d scaled by a quarter or something, and d is the thing we've been talking about, this first derivative that squares to give the second derivative in the Klein-Gordon, and we stick this thing here in that squares to -1, then what we get out is in fact a Clifford algebra expression, which is a solution to the Dirac equation. And that Clifford algebra expression has come exactly from g, which is just something that is plugged in, and d, which is just an operator that you're sticking in, and then the actual thing, r. So it really only comes from R. So what this
Yeah.
equation tells you is that the four-dimensional Rodin lattice satisfies the Dirac equation.
Yeah, that's pretty much what it comes down to. It uniquely specifies a solution to the Dirac equation, and that means that it encodes not just relativity and physics, but also fermions.
Right.
You know, so it's
Right,
not
so
just not just a theory of force, but also a theory of matter.
Exactly, exactly. So this equation here, even though you might not understand what it is, what it means is that the four-dimensional Rodin lattice behaves like matter, as well as behaving like radiation, which is maybe not radiation, but like force carriers. You know,
Yeah, force carriers, yeah.
Bosons, which are the Klein-Gordon particles, they're flying around between the matter, carrying energy and making things move around. You know, most of the things that you see in the world around you are only a tiny fraction of the energy of the universe. There you go, Sedona, but it's true. and that tiny fraction is basically electrons emitting photons and catching them again. And that's pretty much everything that we experience. We don't really experience, at least to our knowledge, the stuff underneath, right, Rowan?
I certainly agree. I don't, at least.
But and the dark matter, well, I have a new idea about dark matter, but I'll have to wait to December.
Okay.
It involves superdeterminism. But anyway,
Okay.
So you won't like it.
Well, it's
you think that quantum theory is you know, the Bell's theorem. But anyway. Let's not get distracted.
Yeah, let's not get distracted. Yeah.
This equation here is the Rodin four-dimensional Rodin space-time equation that is expressing the dynamics of matter.
Yeah, that's exactly what it is.
Not just the dynamics of the energy that's traveling between matter to change its state. The latter coming from the Klein-Gordon equation. Now, this is where maybe it gets more interesting for the audience, because at this point, what Rowan's going to do is go, "Wow, what do you think about that then?"
Pretty much. I didn't want to tell it what to think, but I understood that it clearly understands the mathematics accurately. So now I'm not going to tell it that this is profound and world-changing. I'm going to say, you know, what do you think? And see what it says.
And before we do that, do we need to say something about this? Yeah, sure.
Please go ahead. Yeah.
Okay. While you guys were describing that, I got inspired to work with ChatGPT on something, and I think you're going to like it. First of all, but before we do that, I just want to say to those who don't know anything about the Dirac equation, basically it's a second order equation, as all wave equations are. In other words, the second derivative of space is somehow equal to the second derivative of time. And
no, that's a Klein-Gordon.
Well, right. Well, it's also the Dirac equation, because we're looking at the E equals mc squared plus pc, that whole thing squared, and you got this squared thing, and you want to find a first order equation for it. That's what Dirac is all about, and that's how he came up with this. So he found a way, and I don't want to get into too much of it, but it's by using something called the Pauli matrices, which allow you to make a first order thing out of a second order equation. It's unbelievably brilliant. But the point is, there was something called the Pauli matrices. There's three special matrices, and they're useful in quantum mechanics. They're useful in a lot of things. And so I've been working for the last half hour on this idea that if you recall, way back when you first got started, Tony, you talked about these, you gave these three 3x3 matrices, which are kind of the seed, if you will, for the shear maps. You remember what I'm talking about?
Yeah.
Well, I thought, is there a correspondence between these three matrices and the three Pauli matrices? And it turns out there is, and I just derived it. I just was able to get it from, I had a little help from ChatGPT, but basically you do a little transformation, and you can get from those three matrices, although you have to flip that second one around, like I said, and then you get exactly the three Pauli matrices. I thought that was pretty stinking cool. So there's a
Wow.
one-to-one correspondence for sure. Does that make sense what I'm saying? I can say
It
Yeah,
makes
well,
sense.
it
It's
makes
actually quite impressive. Yeah.
yeah, and it wasn't that hard. Once I just thought of the idea, I thought there's got to be a relationship, and and sure enough, there is. So I can send it to you. I mean, I got it right here if you want to.
You know, in the Clifford algebra, in the Clifford algebra formulation
Well,
of the poly.
yeah,
the poly
what I did
matrices-
was I found a 3x2 matrix, which is composed of two vectors, and the two vectors are really simple. They're just if you can imagine the 3 points from the real part 1, and the other two are real part minus a half, and imaginary part plus or minus square root of 3/2. It's the 3 points, which are the 120 degrees apart. You with me? So those two vector, I have the real vector and the imaginary vector, and that's my transformation vector. I multiply that by, I call them M1, M2, and M3. And I did one more scaling thing because the original vectors are not normalized. They have 1,
Right,
2, and
yeah.
4, done, do, and door. That's not a normal vector. So
Yeah.
I had to scale them, one of them by 4, one of them by square root of 7. But then I doing that normalization and everything, that I was able to get the correspondence between those three matrices and the Pauli matrices. So I think that's a big deal.
Greg, I think here's what I think you have to look at. Those three 3x3 tiles correspond to xt, yt, and zt, but the Pauli matrices correspond to xz, xy, and yz because they're spatial rotations.
Okay.
So it could be that actually is also true. And what you've picked up is that the structure is repeated for space-time as it is for space-space. I don't know. You'd have to do the calculation. Yeah,
I don't know, but I'm kind of excited about it. I'll send it to you. I mean, I can show you right now if you want to look at it.
No, because we'll get distracted and we won't.
Yeah, I get it. But anyway, I was excited about that, so I'll let it go, and you guys go on. And yes, I'm listening.
Okay.
You were wondering about that. So.
Can you tell us how the audience looks? It's terrible giving talks when you can't see people's faces, actually.
Yeah, you have no idea whether people understand it or not.
or how they would prefer to hear it. That's kind of the thing.
Yeah.
But let's look at the summary, right? The specific R gives us the Klein-Gordon with the differential operator defined as in Clifford algebras the way Dirac did it, and we rescale it. We get the Dirac form there, and we get a solution. And square of that solution reproduces the discrete callback-Leiber, the discrete Klein-Gordon equation. So ChatGPT 5 Pro seems to agree with your proof, Ruadhan. And now you say, can you comment on the significance of such a simple formula for R yielding full rank solutions to the Klein-Gordon and Dirac equations? And here, it thinks about this for 8 minutes. You got 8, I've never had GPT thinking for 8 minutes. So what, do you ever imagine what is it doing in those 8 minutes? It's literally just activating this huge network of like associations all over the place. It's really doing a phenomenal thing. It's an amazing thing.
You can see its thoughts. Yeah. It gives commentary on what it's thinking about during the process, but then it takes it away at the end.
Yeah, you can see the chain of thought. I know. You pretty much have to copy and paste what is there.
Yeah.
So it's surprisingly powerful that Marko Rodin's 4-dimensional map, well, a linear form times a checkerboard phase already yields exact solutions of those two equations. Here's why that simplicity matters. There's a lot of technical stuff in here. Spectral.
Yeah, it might even be a bit boring unless people want to know about Brillouin zones. It could be a little bit boring to go through too much of this, but I mean, just the titles though and the significance sections, I think those would
okay, yeah, the Brillouin zone. Well, for people who like sending energy into crystals, there might be some people in Sedona who like that.
Okay, yeah. Yeah, those people might be.
But no, the
good
Brillouin
ideas.
zone actually it's practically a new age idea. It basically means that that you put in a wavelength into a crystal that has exactly the same frequency as the spacing of the elements of the crystal. And that's why they call it the Nyquist mode, right? Because you get a resonance that is at the highest possible frequency that the material can support. Right?
Yeah, I think the technical definition of a Brillouin zone is it's the central cell in the Wigner-Seitz lattice or something like that. Essentially, there's a bounded inside a lattice. You can't have waves of every frequency because things have to repeat after a certain boundary or something like this. And so you have essentially a little a range of wave space, a small little section of wave space called a zone, where the wave number of the wave lives inside this zone, or the wave vector of it lives inside this zone. And this the edges of the Brillouin zone here, I think it says, what does it say? It's the corner of the Brillouin zone. So it says that this particular wave is the wave that exists at exactly the corner of that zone, which I think aligns exactly with what you were saying, where it matches up perfectly with the size of the wave, the wavelength matches up exactly with the lattice spacing.
Right. So it's Marko's, diamond lattice. That's what it is.
I think so, yeah.
It's a plus minus checkerboard pattern that is latent in the structure. That's the frequency zone. And so it's talking about that just in a different way from how Marko would, actually. Basically, that's the Brillouin zone. Do you want to go through this?
Maybe skip the Brillouin zone part because
okay.
I mean, to be honest, I don't know. Going through a lot of the very detailed mathematics could be boring, but
yeah, it could be. But we want to get to the juicy. We want to get to the juicy bits where it says.
Yeah, to be honest, actually, I mean, I think this is it's an informative and accurate answer that it gave in that case. But I think the next answer that I gave, because I wasn't really satisfied with this, it was a bit dry and a bit mathematical. I wanted to talk about physics rather than mathematics, and it gave me a mathematical answer that time. So the next prompt I gave was to say something more about physics.
We'll just summarize. Number 2 is about talking about why 9 is the right number for this stuff. That might be interesting. But section 3 is talking about you've got 2 things in your formula. You've got the checkerboard pattern, which is the 1 minus 1 raised to a power, and you've got this linear equation, a times x plus b times y, and this this is what it calls the linear envelope, and the one that is coming in the Rodin lattice, the linear envelope is the lowest degree choice that both one keeps R and eigenfunction of the D'Alembert. That's just basically saying that the Klein-Gordon equation is true. And supplies a non-zero first derivative, so the Dirac construction works. It's the simplest generator of Dirac solutions from Klein-Gordon data. So translated, I think I can say translated that as saying that the Rodin 4-dimensional Rodin lattice is the simplest Klein-Gordon Dirac thing, right?
I think so. Yeah. There's anything simpler than that is just literally nothing at all. It's just trivial, something that vanishes and becomes zero.
Right.
This is the first non-zero thing that satisfies it.
Right. So there's nothing at all, and then there's the Rodin map in 4 dimensions, and then there's all the more complicated things which are like physics, right?
Yeah. Exactly.
That's why it's interesting.
They may have the Rodin map inside them in some way. We don't know yet.
That's right. The Rodin map isn't interesting because it solves all of physics. At least from what we've done, it doesn't do that really at all. It doesn't have complex numbers, doesn't have lots and lots of things, but it's the simplest thing that has these things in it: space-time, Klein-Gordon, and Dirac. Yeah, and that's
it won't allow you to calculate a probability, but I think it will allow you to evaluate if you have an algebraic equation and you think it might describe physics. You can try to see whether it fits the Rodin lattice, and if it doesn't, then it doesn't describe physics.
Right, exactly. You can use it as a kind of a test case for whether or not something is actually physical.
Yeah, or yeah.
And then he's going on to say full rank in the precise sense. Full rank means 147. It means that each of the spatial directions and the time direction are doing different things in the way that we've described.
Yeah, if it wasn't that way, if say for example, if it was 1x plus 1y, then that would be 1 multiplied by x plus y, which means that x and y would no longer be distinguishable directions in space. They would just be treated as equivalent. Only the sum x plus y would matter at all.
Right, exactly. Relating to lattice fermions. Well, yeah, when they simulate these things, these fermions, they actually build these discrete lattices actually like this, but obviously with more complicated stuff packed into them, right? So I think that's what 5 is about.
Yeah.
6 is telling us that that we have some practical payoffs.
Yes.
Bottom line, the too simple formula is not an accident. It sits at the intersection of a Nyquist lattice eigenmode, number theoretic choice of modulus. So the mass shell, mass being 1, fits modulo n, and that's the thing where it equals 8 instead of equaling, where the Klein-Gordon equation equals 8, which is really -1. And or 8 times r, basically, which is -1r. And a minimal polynomial envelope, which is the one that Ruadhan developed, and that describes the Ruadhan lattice, that turns the Klein-Gordon eigenmode into a bona fide Dirac solution. That's why it gives full rank algebraic clean solutions with almost no machinery. All right, now it's starting to get complementary, right?
Maybe, yeah.
It's starting to go, yeah, that's pretty good. That's pretty good. Now, Ruadhan says, consider that the Klein-Gordon, especially the Dirac equation, encode principles of both special relativity and quantum physics. The function R therefore seems to also encode principles of relativity and quantum physics in a minimal form. Are there any insights into physics achievable by studying such a simple object that encodes the principles of modern physics? Good one. Absolutely. Thought for nearly 5 minutes. Absolutely. Now it's getting enthusiastic. Do you want to talk through this bit, or shall I?
I mean, I think I'd probably say the same things as you would. I don't know if I would go through all of the mathematics exactly. Well, maybe reading. It depends on what's worth reading. Some of it is worth reading out. Some of it is a bit too abstract, I think. But
yeah,
I think sorry, go ahead.
No, the problem is that I have to read it out to work out whether it's worth reading out.
Exactly, yeah, that's the same here. But I think the titles I think are great, because it says relativity from pure combinatorics, no calculus needed. That's exactly one of the things that's extremely striking. Was extremely striking for me. I didn't have to tell it that was a striking thing. It realized on its own that was the most striking thing that should be listed as number 1. You get essentially the theory of well, I can't say you get the whole theory of relativity. You get something which is consistent and encodes the principles of the theory of relativity, and you don't need any of the fancy mathematics. You don't even need spatial dimensions. You don't need continuity.
Right.
You don't need calculus. So it's you don't need as it's saying these things can be expressed in purely combinatorial forms or combinatorial terms.
Basically, it's saying it's kind of saying we don't need Minkowski distance.
Yeah.
We don't actually need to define a metric space with a Minkowski metric and measure distances in it to get the effects which obey the gauge invariances of that space.
Yeah. Well, at the most, what we need is a signature and this number pattern, and the number pattern is generates a signature. In fact,
we don't have a signature in here. We didn't put a signature in here.
We didn't introduce it. It came out of the number pattern.
The signature came out of the number pattern. That's incredible.
Yeah. So yeah, that's true. So that's
Well done.
number one. Yeah, and I think number two, that's it. The second one here is quantum. The quantum part of it is obviously, hugely important. Like basically just this, the phase, the fact that, we started off with this checkerboard where you just move, anytime you move in a direction, you just make an increment, moving in the X direction, you add 1, moving in the T direction, you add 3, and so on. That if you start off with that and then you just add in the phases, you just add this -1 + 1, the checkerboard pattern, that produces essentially quantum wave behavior as it describes it. So, and it not just like the minimal characteristics, but it actually satisfies the equation, the Klein-Gordon equation and the Dirac equation. You get all of that quantum mechanics just from a simple checkerboard pattern. It's quite astonishing, because when we think of quantum mechanics, it has all of this complicated machinery. It has a Hilbert space. It has these complex rules for specifying probabilities and so on, and transition rates, inner products, and all of the linear algebra that's involved. And this is an extremely minimal pattern that manages to encode all of basically at least enough of quantum mechanics that you can say that it satisfies the Dirac and Klein-Gordon equations. So it's actually very impressive.
It if you do say so, it shows that space-time and the two main equations of quantum field theory that govern matter and its interactions are trivial.
Does it actually say
now
that?
You could come back and say, so that's so they're just properties of general things. So what you could have discovered is not interesting, but actually discovering the fact that those things are trivial is very non-trivial.
Yeah,
I think
it's true. And yeah, I think section 3, like why the linear envelope matters and is minimal. I don't know if that's going to make that much sense to the audience, because although it actually is just things that we've already said, in other words.
It means that you can't just have the checkerboard pattern. You have to have the checkerboard pattern with a particular arrangement of the space-time axes, a particular properties of the space-time axes. Actually, those properties of the space-time axes are the things that give rise to the Minkowski signature. The signature comes from 1473. If you put something else in there, you would get a different arrangement of integers on the grid, and you wouldn't have that signature property. So
I think that's true. But in Mod-9, though, you don't really have any other choices. Those are the choices that you're basically using all the numbers that there are available to use. Right. When you write it in that form.
Yeah, if you just said the checkerboard, you wouldn't have Minkowski space. So in Minkowski space, the signature comes from 1473, basically. Yeah. That's what it comes from. So that, actually, I didn't understand that before, but that's definitely interesting, because that relates the signature intrinsically to like number theory, right? And groups. It relates the signature to group properties of, well, it relates them to Mod-9 arithmetic, the cyclic group of 9, basically. If you were to take that other solution that uniquely and consistently can tile the space, the one that Greg would find interesting, possibly because it's C3 times C3, that wouldn't have this signature structure, would have something else.
It's true, actually, yeah. I did continue on that chat after I sent it to you, where the AI was confirming that this was the second solution. This is the thing that I remembered deriving that solution back in 2018 or 2019 and saying, oh, that's not very interesting, and then forgetting about it. And then when you asked me, is the Rodin tiling, is that the unique way to label things? I was thinking, yes, it's not exactly unique, because I remember finding another solution and I asked ChatGPT, and it came up with the other solution. But what the thing about that solution is that you're absolutely right. It doesn't reproduce. It doesn't distinguish between any direction. Every direction is equivalent to every other direction in that. So what that solution describes is really a way to tile 4-dimensional space with symbols in a way that's compatible with the structure of 4-dimensional space. Whereas what the Rodin map describes is a way to tile 3 plus one-dimensional space-time with a labeling that's compatible with the structure of 3 plus one-dimensional space-time.
Are you sure it's this thing here? It looks to
Yeah,
me
that
like
thing,
it
it
looks
has
to me
no
like it
preferred
breaks it.
directions.
Looks like it breaks it into two different sets. The diagonal one and the straight one.
Yeah, but if you add any three, if you take 3 steps in any direction, defined by those directions there, you get back to 0, 0. And whereas with the Rodin map, you take 9 steps in one direction and 6 steps in another direction. So with that map, with that system there, every direction is equivalent to every other direction. No matter what direction you go in, it's always 3 steps to get back to where you started.
Right. Good. All right. We've done the number 3. It thinks that the linear the number 4 parameter full rank solution space. Yes, we got that. You recover the right number of degrees of freedom for a minimal Dirac sector from an object you can write on a napkin. This is a sharp algebraic reflection of the spin. Oh yeah, spin half. You see, the thing is, we don't really have an electron sitting there. We just got a wave function. But all this stuff about you know, fermions having fractional spins and bosons having integer spins, those are all things that we don't understand in this framework yet, right?
I guess we don't. What we do understand is that it does satisfy the equation, so it does encode the concept of a fermion somehow.
Right, right. I have a feeling that we should have kept on working on this.
I know.
But you went off to try to solve AI, huh?
Well, actually, I was thinking about the brain,
That's
and
right.
I was looking for this pattern in primary visual cortex.
Yeah.
And so on,
Anyway.
looking for patches. I found never mind. That's a topic for another time. It is fascinating.
We have to forget. This is not just a normal conversation between us.
Yeah.
It's a talk. So number 5, number theory is a dial for physics. Yeah, there we go.
Yeah, I think that title is just perfect because it's exactly it's very succinctly explains the significance. I didn't tell it that, hey, you know, this is number theory is a dial for physics. It said that itself.
Finite arithmetic plus lattice gives a controlled sandbox where dispersions, masses, and symmetries are arithmetic congruences. Yeah. Things like masses and dispersions and symmetries are just numbers, relationships between numbers.
Yeah.
You know, that's amazing. Clarify which features are structural, topological, algebraic versus analytic. Yeah, because we're not working in the continuum here. Yet we're getting the things that people are talking about in the continuum. So that's what this sentence is about. That we can find out, we can separate the topological algebraic things from the analytic things. Yeah, that just means that, how would you translate that? It's just saying that
it's not smooth because it's discrete. It has algebraic structures. You can write equations and so on, but you don't have analysis in the usual sense. You don't have infinitesimal distances dy dx, where those things are actually, instead you have discrete differences.
Right, so it's a bit like pulling some seaweed, right? We pulled some seaweed and we yanked out of quantum field theory and special relativity all the stuff that has nothing to do with you know, continuous space-time, but it's just built into number relations.
Yeah.
This tells us that it should be used in the classroom.
Pretty much.
Do you have anything to say about number 7?
Yeah, I think this is kind of what was on my mind when you told me that this equation, or that the formula satisfied the Klein-Gordon equation initially. I thought, No, it doesn't. It shouldn't. You know, if that's true, then that's very new and interesting, because that's not exactly not what you would expect at all. And the reason is because of what it says in 7, basically that replacing the complex numbers by a ring of integers is dismissed as too crude. And that was where I came from in physics, essentially thinking that no, what you need to probe the full structure of physical theories is a continuous thing. It has to extend through space. It has to have waves and continuous numbers and so on. And that if you try to get anything simpler than that with smaller systems, then you'd lose all the interesting structure. And what 7 here is just saying is that you don't. Exactly what it says. It says core kinematics survive the causal structure, factorization into a Dirac operator, plane wave eigenbehavior, and spinor emergence. Those are exactly the things that when you told me that it satisfies the Klein-Gordon equation, I was thinking, well, if it does that, then it should have all these other connections, and I thought it's highly unlikely that it does until we studied it and found a solution to the Dirac equation. So yeah, I mean that's basically just saying that it's you would not expect this to happen. You would not expect this to survive in such a simple system.
When you go to the rest of the standard model that's above the electrons, right? You go into the weak sector where you have a symmetry breaking, and you start to get more numbers for every fermion that looks a little bit like an electron. And then you go to the strong sector, which is the particles inside the nucleus. The bosons are the gluons, and the fermions are the quarks. You can get like 32 different numbers, to describe something. Rather than just one number, a scalar particle solution to the Klein-Gordon equation of one number for each point in space-time for that thing. But you get 32 numbers or 16 numbers or 24 numbers. When you go to these more complicated parts of particle physics, it does make me wonder, and this is of course probably what we wanted, right? Back 6 years ago, how much of that comes out of the same kind of combinatorics, just applied in a more sophisticated way.
It's true. It could. I don't know. I think there's a question later on, or something. I think later on in this answer, it says something about you could turn on gauge fields and see how the numbers change after that. And that's something that had been like on my mind a little bit before, but I never actually did it because it seemed like a complicated task, and it seemed like there were other more elementary things I didn't understand yet. So, but I think it probably is the case. And also, like it mentions curvature, the way that these numbers are going to behave on curved surfaces. I just can't help the feeling that that's got some kind of connection. It will have some kind of connection to general relativity or gravity.
Yeah, I don't like it. The Cambridge people that do a lot of Clifford algebra stuff, their version of general relativity is in a flat Minkowski space. They just play with the gauge. They keep the space flat, and they just morph the relationships between things so it looks like a normal special relativity world, but with complicated interactions.
Yeah, I think I've seen that. I think they call it hyperparallel theories or something like that. And it's a way of approaching it.
I don't like the curved space-time thing. I think that that something like that is probably a better way to do it. Who knows? Gravity. It's difficult, right?
Yeah, it is. Yeah, famously.
Yeah. What can we do with our build benchmarks? I don't really know how I would do that.
I'm not sure either. But this is what I was talking about: curvature and gauge probes. Turn on background link faces and see how the identities deform. So that's that's another thing, another area of investigation I haven't even gone into yet. How do these numbers change when you interfere with them?
Right. Yeah. So far, the Rodin lattice is just sitting there like a frozen eternal thing.
Yeah.
It's that comes to, because in the end you want to have particles and forces and inhomogeneous distributions of stuff, and you want to understand how three-dimensional rotational symmetry can exist. And so it really is, you know, it really is, this really is just a beginning. If it's either a very useful toy or it's the beginning of a research program, I think.
Yeah.
But it would only be the beginning of a research program if it is in fact a research program. Something about math shells. Use it to teach kids.
Yeah, I think that's actually, it is a good gentle introduction. If somebody's going to be learning about quantum field theory, Clifford algebras, quantum mechanics, and relativity, showing them this is kind of a gentle introduction before you really hit them with the mind-bending concepts that are going to require some thought.
And they might then, you know, turn those mind-bending concepts into something simple if they start there. Choice of G, we've been arguing about that. I think it has to be this. It has to be 1, 2, 3, not 0, 1, 2, 3, 4. Well, this G thing has to square to -1, but in Clifford algebras, there's loads of things that can square to -1, right? Like here we are in Minkowski space. I'm just going to write E sub 1, 2, 3, and going to square it. It's -1, and this one here is -1, 2 also. So in fact, E1 is going to be E1 squared is going to be minus. Oh, that's 1. So 4. So there's lots of different things in Clifford algebra that square to -1. So if you get this need to have something square to -1, you actually get to choose which one. If it was just complex numbers, you could only choose I. But in Clifford algebras, you get to choose something. And so actually, while we were preparing this, we were arguing about whether it should be E1, 2, 3 or E1, 2, 3, 4, which here is written as E0, 1, 2, 3. And I think that I was arguing that it has to be this, because then if it was this, then you would end up with a wave function that had terms of different terms that were of odd grade and even grade in them, and then the Dirac equation solutions in the normal physics literature that uses Clifford algebras, you only get even grade. But so this our Dirac equation doesn't really map onto the physics Dirac equation very well yet. It just has the same square root of the Klein-Gordon structure that we get in the normal physics.
Right, it is a valid solution to the Dirac equation, but the question of what do you replace I by in the Dirac equation it's ambiguous when you have a Clifford algebra, because there are multiple things that square to -1.
Yeah, but the Cambridge people that do Clifford algebras and the Hessenis who inspired them, Chris Duran, all those kind of people, they are using this as far as I remember. Okay. Right, so the bottom line is R is generally insightful. It shows how relativistic kinematics and quantum interference can be encoded in the smallest possible algebraic pattern, a checkerboard phase and a linear envelope living in a finite ring. From there, you can derive Dirac solutions, test lattice ideas exactly, and use modular arithmetic as a clean microscope for what parts of modern physics are fundamentally algebraic and combinatorial. So that's amazing that we're sitting here having an artificial intelligence tell us that we did something all right.
That's true. I think that's, and it's ChatGPT Pro. It spent I don't know how long it spent thinking about that, many minutes, but I think it got the right answer.
Yeah, this was the 8-minute one, wasn't it?
8 minutes, okay. So it thought carefully, and
well, they are very flattering. We have to control for, no, this is only 5 minutes. We have to control for the fact that they're trying to make us feel smart, right?
But they're trying to get you to renew your subscription. But at the same time, it is actually an intelligence. It is actually it does do things like check the equations. It figures out you missed out a factor of 2 here, and so on. It does quibble about your choice of G, and so it does understand. And I think its final result is accurate. I didn't tell it to say that say this is the greatest insight ever, but it certainly understands exactly how important it is.
Right. So that's it. Actually, I don't know how long we've gone. How long have we gone? There maybe are a few other. There are a few other things to wrap up, like in my plan for this. I wanted to say, yeah, we've pretty much said number 10, right? More work needed.
I think so.
Number 10, number 11. We just read it from ChatGPT. It's a new window into the playing field, space-time, and the rules of the game. It's a new window into it. It doesn't prove why the Rodin coil works or anything like that. It doesn't. It doesn't give us a technology for building amazing things. But if people are building those things using some of these ideas and they're working, I don't know or not. It's all the more reason to work this stuff out. I had three kind of bugbears in my mind: the fact that it's discrete, the fact instead of continuous, the fact that it's Mod-9 instead of, continuous wave functions, and the fact that we have a playing field without players. We don't have electrons. We've just got a big number pattern that has wave properties like quantum mechanics in it. So we're missing a bunch of stuff, but that's a start, right?
I think that's pretty good. Yeah, the next step, I guess, is how do we get from a number pattern this simple to a description of multiple interacting particles, and how do you model the different particles? And yeah, we don't know how to model a particle yet. we've got a wave that fills all of space and time. We don't know how to get a particle or get anything localized from this just yet.
I think we have to add something to this. I have some ideas about what to add. We have to talk about it. But I don't think we're going to get to answers. Well, the discrete not continuous, I put that into ChatGPT and it started talking about renormalization group and everything's going to be fine, right?
Of course, yeah, that's what it's going to do. That in physics, that's the attitude. You can discretize. It doesn't matter what grid you discretize on. Once you make the grid points close enough, it all becomes a homogeneous. You imagine it's rotationally invariant, even though you started off with preferred directions.
Right. But even then, like, what does that correspond to? Are we trying to find like a discrete physics at the base of reality? Or are we kind of trying to find a kind of fractal superposition of different Rodin maps at different scales that all add together to give the stuff that we phenomenologically observe? Who knows? One thing I would say is quantum field theory, and you and I, we have not talked about this actually. This is something I've concluded since last time we talked about this. Quantum field theory is very weird. This path integral stuff. Really, what it is, it's a space-time point process. It's a probability distribution over a space-time point process because interaction vertices in quantum field theory. When an electron's coming along and a photon hits it and it changes its energy or direction by absorbing the energy of the photon. There are three things going on there. The photon comes in, the electron comes in, and the electron comes out at a different angle. And if you have four things happening or five things happening, they all can be decomposed into those three things. Something going along and something hits it, basically. And that's called an interaction vertex. Now, all of the stuff that happens in quantum field theory is happening at these interaction vertices. There's nothing happening in between. They put these green functions. They say between this interaction vertex and this one over here, we're going to have a field, and it's going to oscillate all the way through space and time. As a computer scientist, I'm sorry, that's a big waste of voxels. All you need.
Don't even bother to store that because there's no information processing happening.
Exactly. So you might as well just have the interactions and have the relationships between them encoded in some compact form, right?
Yeah, I guess that makes sense. That may also be why the Minkowski distance between two light-like separated events is zero. There's just nothing to describe the separation.
Right, and then the other ones, it's also sort of zero because it's the mass that is playing the role of biasing the Minkowski distance in a way. The mass is, the energy relation is just satisfied with a mass term stuck in. So anyway, and this is when they say that they think that quantum mechanics is stochastic, right? What are they doing? They're firing a bunch of things round and round in a circle in a particle accelerator, and they calculate a thing called a cross section, which is some functional shape which describes a probability distribution. And that probability distribution is made out of zillions and zillions of particles going round and round the circle and bumping into each other, right?
Right.
Why do they think that it's a probability distribution? Any other place you do that in science, the probability distribution is just a result of
noise.
It's a result of some particular things happening. And
okay, so yeah, I can explain why. I can explain why that is. So it has to do with quantum entanglement. So if you have two entangled pairs that are separated by a distance that's so large.
Brian, we shouldn't actually do this, because this conversation lasts for an hour and we end up not agreeing with each other.
Okay. But I'll just give you a brief summary of what the theorem is. The theorem is that in certain quantum measurements, we can prove that it's not possible to make a prediction more accurate than the predictions of quantum mechanics, which are statistical. That if you could predict the results of experiments better than quantum mechanics, you would be able to send signals backwards in time, and you'll be able to cause a paradox.
That's fine. You can have. I don't think it's paradoxical to have. Let's imagine that instead of what he's talking about is that Bell's theorem is true as long as you rule out a thing called superdeterminism. And what is superdeterminism? It's just determinism. It's just saying that rather than just having things bump into each other and cause deterministic reactions like a billiard balls on the table, what you really have is a determinism that extends over space and time, as if it's one huge big equation, like one huge big thing, all constraining itself into one solution. Everything that ever happened and ever will happen constrained into one huge big thing that happens. And anytime,
yes, but just to say something, it's even more expansive than that. It means that even our choices about what measurements to make have to be determined ahead of time. So in the Bell's inequalities with the quantum non-locality thing, these non-local effects, in order to presume that those are really happening, something is really happening across vast distances of space, you need to presume that people have free will and that their choices are not predetermined by something that happened before, that they have the ability to make a different choice. And superdeterminism supposes that there's this entanglement between the choices and results of one experimenter and the choices and results of another experimenter come from entanglement between the choices, because both the choices of the experimenters were determined by things that happened long in the past. So the experimenters don't really have free will, and the experimenters couldn't have made a different choice that would have violated the results of quantum or the predictions of quantum mechanics.
Yeah, that's right. That's what's happening. I mean, doesn't make logical sense to conflate free will with indeterminism. There's no logical connection between those two concepts.
It's true. So hyperdeterminism as an explanation for quantum non-locality is basically the idea that it's not just the physics, the results of the experiments, but also our own personal choices that are so fixed in advance that they've been fixed in advance to arrange the physical results to come out exactly in this way that's compatible with quantum mechanics.
That's the Scott Aronson kind of conspiracy theory version of it. It's a bit of a straw man. If you have one big equation that everything satisfies, then it's not a conspiracy that some variable over here is consistent with some variable over here. It's built into the solution of the equation. It's not something that is a implausible accidental arrangement. It's something which is an exact consequence of the fact that one thing happened.
It's true. It's just nobody can disprove that point of view, but I think most physicists would say that it runs counter to their intuition to say that a physicist doesn't have the freedom to set, his measuring instruments to whatever he wants, and that's not a variable that should be treated freely.
Well, there's a lot of things in life that are counter to our intuition. The experience, the psychological experience of uncertainty is not necessarily related to indeterminism. It's a psychological phenomenon, like any other.
Of course, it's lack of information.
It's explained by things that that are not available to your psychological insight quite often.
It's true. Yeah.
I'm not sure why I went off on that, but anyway,
Yeah,
the
I don't
idea,
know. Maybe yeah.
here's why I brought that up, right? We have the problem of going from this Rodin lattice stuff into some future work where we explain what's really happening in quantum field theory. In order to do that best, in my mind, we should really understand, and probably Greg would agree with us, what the quantum field theory is really talking about. And if it's in fact talking about a set of discrete, if it's a point process, if quantum field theory is really talking about something which is one big set of interactions that are consistent with each other, then what you have to find is the consistency relationships that determine the exact form of the solution. Now, what do we have of that so far? We've got a bunch. We've got some of them, you know, energy momentum conservation and spin and charge conservation and all kind of things like that. And those are the things that have to be satisfied at vertices of the quantum field interaction, space-time interaction. But what if there's some other ones? What if there's some stuff in preons, in quarks or something like that, or gluons, and you know, other topological things that come out of playing with the number theory, right? Higher number theoretical symmetries that we haven't spotted yet. If we put those in, we might get more constraints on an interaction vertex than we have using the standard quantum field theory tools. And then we might be able to justify the extra constraints, which would be required to turn quantum field theory from a stochastic into a deterministic theory.
Okay. Yes. I mean, it's conceivable. Yeah. But even if we did that, we still wouldn't be allowed to signal backwards in time. It would still remain exactly as it is. The behavior of quantum non-locality and so on. It wouldn't.
You have to distinguish. You have to distinguish signaling from you know, from what's it called, mathematical.
From having an effect.
A mathematic from. If I write out one equation that the whole universe is satisfied, that doesn't mean that all the correlations that are induced by it are carried by photons between the different parts. So it's not really signaling, it's just a correlation that exists due to the equations that determine the form of the thing.
Okay, yep. I don't disagree. From that's compatible with the hyperdeterministic viewpoint. So yeah.
Well, I only said that because if you want to say how you're going forward, we should probably have
as a question. Do not take this.
What? Is there a question? Or I was about to wrap up and say that those were just some thoughts about how to take it a bit further.
Okay. Tony O'Flanagan, can you guys hear me? Hello?
I can't really hear. I could hear a voice in the background, but
we're going to turn up my mic in a second.
Okay.
Hello, this is Marco saying hello to everybody. We're testing my audio. We're setting my audio. Tell me when it's good. When is it good?
It's all good.
It's all good. Okay, Giselle over there, the librarian from the Patrick Flanagan Librarian is here tonight. Yay! And she's in charge of the mic. So anybody who has a question can get her eye, and she'll come over with the mic with you. She won't let go of it. I learned this a long time at Tesla Tech. Okay, from Mr. 𝗵𝗲 Sr. We learned once we handed him the mic, and we love him very much, and he's ascended in heaven now. And it took us 45 minutes to get it out of his hand, and nobody wanted to jump him. Okay, because he was a senior citizen, and we all love him. So Giselle keeps the mic. Anybody have any questions? Nobody. Nobody's brave enough to try to challenge the stars. Okay. I'll even put our tech on this hot seat. John, you're a computer scientist. Do you have any questions? He's good.
We have a question over here.
We have a question over here. And who did you say to that I missed? Go ahead, Giselle. And then we're going to ask the, we're going to stump the panel, okay? This person is not stressing out over here, is he? We're going to stump the panel. Okay, but first Giselle's going to take the mic to, there he goes.
Hello, could
This is Danny. Hi, Danny.
hi. Could you please summarize your talk in simple terms and equate it to Marko Rodin's work in simple terms for the masses? Thank you.
I think if that's the question, we definitely failed.
Yeah, I think that's what this was.
I thought we said it, but here's oh, keep doing that. There's Marko's thing, right?
We don't see it. Oh,
you
the chat room sees it. This live stream does it, but we don't see it on the screen here. Is there any way, Lisa or John, you can bring it up for us? They're going to bring it up in a second. There it is. Got it.
Yeah, there's Marko's thing. That's numbers on a torus that Marko's been talking about for many years. And what we did, instead of putting those numbers into on the surface of a torus, we put it into a four-dimensional grid. And we did that by taking this patch here from this torus. And the second patch we took from this torus. And the third patch we took from this torus. And we called those X and time, Y and time, and Z and time. And then out of those three slices that we took from the three possible Rodin toruses, we built a four-dimensional Rodin grid, where there, instead of a two-dimensional surface of numbers, there's a four-dimensional space with the same kind of numbers happening in them. And what that four-dimensional space looks like is like this, right? This is one example of four-dimensional this would be one single surface of one torus, right? But when we put when we slice those toruses into, we literally cut the donut and turn it into a sheet. We get this sheet. We stack those sheets together. We get a cube. When we stack those cubes together, we get a four-dimensional cube. And that four-dimensional cube is the three dimensions of space and the one dimension of time. And then what we did was we found a formula for that space-time Marko Rodin space, which is just a four-dimensional one instead of a two-dimensional one. We found a formula for it. And then I went off and I started adding and subtracting bits of that formula and discovered that some basic physics equations were true on that in that four-dimensional space, and that the structure of space-time was also in that four-dimensional space. So what we did is we extended Marko's work from 2 dimensions to 4 and showed that basic physics exists in it.
Okay, what I'm going to do next is I'm going to ask you to respond to Phil, and Phil has some things to say, but I'm going to hold it to 9 minutes with Phil. Then I'm going to go to 𝗓𝗲. I'm going to give you a maximum of 9 minutes. Now, bear in mind that when you're done, we've covered everybody, you can come back. Then I'm going to go to 𝑔regg for 9 minutes. You can be shorter if you want, you don't have to be long. And then, give me 1 second. In the chat room, if somebody else wants to make a comment, ask to be let in. That's how you do it. And Lisa and John will invite you and bring you to the front of the line. Okay, so Phil, take over.
Oh, can I ask a question? I've been trying to get the mic for the last 20 minutes.
Phil, do you mind?
Sorry.
He says after you.
Okay. I wanted to address your question about discrete versus continuous. That was about 20 minutes ago you talked about that. You recall that conversation? Okay.
Yep.
So here's a thought. This is what fractals allow us to do. If you think of something being discrete at the highest level, but then it's fractal, then it's discrete at the next level, and it's discrete at the next level, and discrete at the next level. It's always discrete, and yet it's a fractal, so it's continuous in the end result. And I believe that is a really good, that is a way that we could think about applying these numbers. If they satisfy a certain equation on one level, and then on another and another, eventually they also satisfy a continuum. And I just like to invite thinking about it in that way.
Yeah, I think that's absolutely accurate. And yeah, that's kind of what I was thinking as well. It is discrete, but because of this fractal nature of it, you can take two numbers and fill in all the numbers in between, zoom in and find any of those two numbers and fill in numbers in between those. You do have ultimately a continuum.
A self-healing continuum, because you can take a chunk out of it. You can take a chunk out of it anywhere and it'll repair itself.
It's true. If you could take a lump out and glue the edges together, and it's like nothing was ever missing.
Yeah.
So that's actually that makes it very suitable for constructing different topologies. You can bend it around on itself. You can take chunks out of it. It's almost like a substance that you can take. You can form. You can make can you make a sphere out of it? I don't know.
It's a Terminator.
It's a Terminator. Okay. Yeah, but absolutely. The thing is that what I know how to do is I know how to differentiate. I mean, I know how to calculate a rate of change of a function when I know that like there's this it's the function at this point and at this point, and I'm interested in the difference between the function here and there. I know how to do that, and in normal if we were using normal numbers, like real numbers, then we know how to do calculus. We can take extremely small distances, and we can take a limit, and everything looks very nice in the limit. As things get smaller and smaller, the numbers get closer and closer to a single number. But what happens with this number map is that when you go smaller and smaller, the differences still remain significant. You no matter how, when you have like I don't know, say a 1 and a 2, and you zoom in and you find a lot of numbers in between those, and you zoom in and you find numbers between those, the numbers don't get closer and closer together as you keep zooming in. You have discrete numbers like 5 and 6 and 7, and the distance between them is always at least 1. So you never have this narrowing in that you get in calculus. So there's no way, it's just that the limit, you can't exactly say that it converges to a limit as you get smaller and smaller. There's always more detail as you get smaller and smaller, which makes it harder to do calculus. So the equations that we get, from the Klein-Gordon equation and the Dirac equation, the things that we use in physics, they rely on saying the difference between here and here is this much, and you can't zoom it into 0. It's like the structure never stops. It never stops being fully structured as you get smaller and smaller because you're using a discrete system. So I don't know if that explains it, but
it's turtles all the way down. That's what you're saying.
It's turtles all the way down. But with real numbers, these are like kind of smooth turtles. It's more like a snake. And with this, it is like discrete turtles all the way down, and you never get actual continuity. At least, you get continuity.
Phil's screaming in the background. He's screaming in the background. He's acting like an airport. What are those guys with the flags? Okay.
Those guys.
They won't let us control our microphones, so I had the same problem. So yeah, get it turned on, Phil.
You're gonna have to keep talking, Phil, till we know your audio.
Okay,
works.
I'm back. Am I coming through?
Yes.
That's what your voice sounds like.
That's me. Sorry, everyone else.
We'll take it anyway.
Okay.
Sorry, I didn't mean to interject. I just was indicating that I was in mute prison, but please finish that point.
I get it.
Okay, well, since I interrupted, and I'm such a novice.
Can barely hear you, Marko. I'm sorry.
Well, that's not. John blast me. Is it any better? Okay. Wait, I got to make sure.
I can hear you enough, but it's not great.
Oh, hello. No, okay. That's because I'm supposed to use the mic. Hold on for 1 second. I want to make sure there's no feedback from my other mic then. Yeah, I unplugged the 𝗬𝗲 mic.
It's much better when you're close to the mic. Eat the mic.
Okay. What I was saying was, so I like to use the terms hologram, but I don't know. I don't want to abuse the term because it has so many so many professional proper definitions. But I envision this as a quantum hologram, and I envision this as a quantum hypercomputer because of so many shortcuts. If HAL 9000 AI already agreed that this is the most condensed, compressed system ever created, which is true. Okay, and I've got to mute this just to get rid of feedback. Then I call this, Willman uses the definition. I use this as a superlumio hypercomputer, okay? The applications I use this for is I use it for I call it electron harmonic shear. The phrase term doesn't exist, unfortunately. The boundary condition I turn into insulation. I get rid of all noise. This system, have you found anywhere in the, well, you're still learning, we're still looking at the 396, how it's into the internal volume of the torus and how things are all orthogonal or perpendicular or tangential, but I am claiming there is no noise in this system, that this is the ultimate data retainment, preservation. Could we discuss that all together, please?
Yeah, maybe I can have a go at that. So what I say is that as the AI was saying, can everybody hear me?
Yeah, yes. Now I do.
Okay, good. Okay, yeah, so I think just as the AI was saying, this is exact. It's a frictionless system. It's basically perfect in the sense that like there is no loss. So I think you could. I don't know how to build a computer out of it, but maybe if I spent a few years thinking about it, and if I had the assistance of AI and some excellent engineers, it might be possible to build, say, for example, a super efficient wire or a super efficient electronic component in it using, I think as Greg was talking about building ternary computers and how they're more efficient, it may be the case that using 9 can produce a type of excellent extra efficiency. I haven't studied that, but it seems plausible, and the fact that it is essentially frictionless, and the fact that it already solves the equations that we expect physical fields to obey means that we can expect, or I don't know if we can expect, but if we could build a system that was truly a perfect, a three-dimensional spatial perfect replica of the ideal algebraic system represented by the number map, that it would probably have some special physical properties like extreme efficiency, perhaps like resistancelessness, or other things. So that's all perfect. It's a hard word to say.
Okay, the word I use for those circuits, those Mobius circuits, and then Tony, please speak. I refer to the circuits in there's one pair. One goes to the right, one goes to the left, and then you have this, what's the term? But I call this superfluidity in those two circuits. In the classic scientific physics terms, to me, it's superfluid. Okay, 124.875, 124.875, 124.875, it's superfluid as far as I'm concerned. Now, what would you call, because I don't have the right ability to describe it, the 3, 9, 6, and I separate the 9 from the 3 and 6. When 9's positive and 3 and 6 are negative. When 9's negative, 3 and 6 are both positive. I say 9's a control. But that 3, 9, 6, and then it's palindrome because it's opposite, because it's really tangential. It's really not going a straight line over the surface because it's going into the torus. But what would you call that? A scalar, a vector, I'm asking you to educate me. Would you call it a standing wave? What is going on?
I would call it a standing wave. Well, is it standing? It's actually a traveling wave that pervades all of time and space. The actual number map is, and it does it in a minimal way. It's it's frictionless. It's algebraically perfect, and I don't know if I would go as far as calling it a superfluid, because in physics, a superfluid is specifically something, it's a fluid where you can put something into it and then push it a little bit, and it keeps moving and never stops. So it's reminiscent of a superfluid. It's like something that's like, it's a description of something which is
Is the whole
a moving
torus
thing.
is the torus a soliton map? Is it unity? Is it the full definition of unity or equilibrium or balance or harmonic supercoherence?
Yes, it's a form of what you might call supercoherence. What it is you have this perfect system which is an exact solution of these equations, and which is perfectly defined. It can't lose energy. It's exactly perfectly defined. But what it has is the ability to be wrapped around. So you can take this number map, and you can form a cylinder, or you can form a torus, or you can probably form more complicated shapes with it. And each of those shapes is going to be a closed system. I think, for example, you talked before, I think, about whirlwinds and so on, about the fact that in the sky you generally don't see structures, in the atmospheric structures, that just hang around, but a whirlwind is able to just stay there. It's able to just preserve its shape, and that's pretty much because it's an exact wrapping around of this system upon itself, so that when things are going around, the vibration as it goes around exactly matches up with the vibration at the point where it started. So these stable structures can exist, and I think that the ways that you can fold this map onto itself, or wrap it around, compactify itself, and make compact structures like tori from a whole four-dimensional space. I think those things probably have some specific physical properties, like being able to just hang around in the air, the way a whirlwind could just stay there as a stable structure. But I don't know what they all are yet, and I think some of them will be electromagnetic. It's honestly going to take a lot of research. All we found is that it satisfies the basic equations, and further development is going to require insight. I think we do have AI. I'm actually impressed by how well AI understands this, and I think the progress is going to be accelerated in the next few years as people are able to ask AI these kind of questions, because it really does take a lot of thought, and AI can do it in 5 minutes or 8 minutes. So what took myself and Tony 8 months can be done in just a few minutes now by an AI. So I think that's really the way that we're going to be pushing this forward and understanding these things.
Tony, I know you want to say something, and probably then Greg or Phil, if you have something to say. Where's Randy, though? I don't see him. Is he still there? He has 3 kids he has to take care of. If he is, please add him. But, he had to leave. Here's the thing that I want to say is that I hope somebody can identify this in nature already existing. I don't know if you would be looking at carbon or what, or helium, or I don't know how this. Eventually, I hope you equate it to to chemistry, to bonding, molecular coupling. I think it can be. I think it does work in that regard in physics. I'm very grateful for all of you focusing on the physicality of this discovery, and the computer as well, and AI as well. When I'll be satisfied is when it's made into where the processor and the hardware and the algorithms, the software, are one and the same. When this is made into the ultimate perfect quantum computer, I call it a 𝗶𝗨 And I have a lot of things to say, and I'll save it for tomorrow night about the flux fields and stuff like that. Okay, Tony, what did you want to say?
Oh yeah, it's not a very long one. It's just going back to the computer discussion. If you think about a computer, what would be the best computer given what we know about the, what we think we know about the world we live in? The best computer would be a three-dimensional box. You want to solve the packing and the communication problem. It would be a three-dimensional box where everything was talking to its neighbors in a very good way, a very good and full rank kind of way, right? So the best computer would be a three-dimensional box changing in time in some funny way. Now, we don't have a computer like that, but we do have a three-dimensional box changing in time in a funny way. So if we did some more thinking about how to encode state in such a system, because a computer really needs state, it needs memory, and it needs gates and things like that. And the Rodin, four-dimensional Rodin box operating in time, it's just really doing one, it's just moving in a very determined path through state space. Whereas for computation, what you need is if this is like this, we go over here, and if this is like this, we go over here. So you need all that kind of stuff put into that box somehow. But then you could imagine a kind of programming modality which took, you know, some task, and instead of turning it into something in the program to run the CPU and some data stored in the memory, it would be a bit more like a FPGA, floating point gate array, which is a bit like a two-dimensional grid. And so what this future computer, you'd probably have an AI compile whatever task you have into that box in whatever obscure way that the box can do it, and you'd never bother asking it how the box did it. The box is just there doing its amazing optimal possible computing, and you write the program, and some other program turns that into something that runs on the box, and that would be your amazing Rodin type computer. I don't know how it would be superluminal. It could be if the superdeterminism idea that Ro and I were talking about is true, then you know you have all the stuff in that about like no signaling and things like that. But if you did understand the correlation structure of matter, you could exploit that understanding in your computation, and that would make it a quantum computing device.
Grab the
Like
floor.
quiet all of a sudden.
Whoever wants to grab it, grab it.
I guess I'll interject while I can. Great, amazing work, guys. That was very enjoyable. I guess just if I could touch briefly on the subject of modeling a particle in the system. And I think that, yeah, the key to that is going to be in interpreting that every tile group as a standing wave, as I think is being suggested, and you know, how you relate that to traditional field equations. I think the key might be in the shears. And if you think of each shear as representing a plane, right, on like XY, XZ, or ZX axes, and that maybe your point charge is modeled as an interference between motion along those planes, right? And so some food for thought about that, if you're kind of looking at how to think of these numbers and interpret them. Just kind of my own reflections on this have led me to the conclusion that the 9 essentially operates as a longitudinal wave. The 3 and the 6 operate as your transverse magnetic polar perturbations. 3 and 6 are your north and south magnetic polarity. And that the Mobius circuit, quote unquote, 1, 2, 4, 8, 7, 5, bidirectional circuits, you know, they're inverse square. And so that kind of models an electrostatic field. And so I think, having this bidirectional flow of these potentials with, you know, would achieve a kind of equilibrium. So I think that's kind of, that's modeling your electron orbital, in my view. And it is a hybrid of your longitudinal and transverse oscillations. And so I think the numbers are all representing that. And so can I screen share? Is that in my capability here?
It depends. Do you know the secret password or code, or do you have a magic decoder decrypting ring?
Yeah, it's 396, obviously.
Oh, he knew it. He knew it. Okay, 396. Yeah, you have found the hidden crystal. You found me. Okay, go ahead.
All right, cool. So yeah.
What is John saying though? John said something.
You gotta just try it and then tell me what happens.
Oh, sure. Okay. Sorry, I'm a bit. No offense to the boomers.
Oh,
sure.
that's
Here we
what he
go.
meant. You want to share your screen?
Yeah.
Oh, never mind. Forget it. I didn't understand you. Of course you can. Never mind, Rosianna, Dana. Never mind.
All right, hold on. I don't even have permission allowed for this just yet. So. It wants me to quit.
Don't quit.
Okay. Well, I guess never mind with that. So I'll just have to use my hands and be visually descriptive.
Why does it want you to quit? John, do you have to give him control?
I don't have, apparently I don't have permissions for my computer and it wants me to reset before I can screen share.
Why would it do that?
I don't know.
John, can there only be one person sharing a screen at a time? The last person sharing was Tony. Ask Tony to stop sharing his screen.
I did, I think.
Tony, if you go to your screen and stop sharing. It's on, huh?
I'm not sharing.
Yeah, he's not sharing. It's on my end. It wants me to quit to do it. I think I can, it might be helpful for everyone else, but maybe you guys will get what I'm saying.
Let someone else talk and reset and come back.
Okay, all right, sure. Yeah, Greg, why don't you go nuts and
And John will let you back
back
into the room in a second.
Okay, all right.
Something.
All right,
and I don't know
good.
if that's going to solve it, but good luck.
Yeah, thank you. That's a good idea. Yeah, Greg, why don't you go for it?
All right.
You want me to do something? Oh,
Yeah,
sure.
yeah, please.
Well,
wait.
if I can share my screen, I would like to show you what I discovered this evening. I think it's pretty cool. Is this an okay time to do it?
Plug it back into the thing there. I'd like to see that.
All right, I'm going to just click share here. All right.
What's up? There down. I just
All right.
want them next to you.
See, I got to get the right screen. Okay,
Just leave
share.
it there. Next time I'll turn it off.
Okay, hang on, I got a couple things up. All right. Can everybody see the screen here on the right? And
Yep, I can see it. Yep.
Off now?
I have it as section 6 from 3x3 shear matrices to polyform. So it's pretty well known in quantum mechanics and other things. Can everybody hear me?
Yeah, you're perfect. I'm screwing with the
Okay.
mic. Go ahead, Greg. I'm sorry.
Okay, I'm just going ahead. All right, it's
Termites.
pretty
So
well
it's termites.
understood that there are 3 primary matrices that are called, given the name sigma, that's just tradition, and they represent,
Wow,
they
you
have
did a
certain
whole paper
properties.
on it.
There's 3 of them, and along with the identity matrix, which is called I, it's just a 1 on the 1, 1 and the 2, 2 locations. They form a basis for all the possible things you can get with 4 matrices. But anyway, if you take any 2 of those matrices and multiply them together, you get I times the third one. And that and they're also kind of related to rotation in that the order matters and things like that. Anyway, I don't want to get into too much detail about what they are, but I think it's fair to say that they're very useful and foundational to understanding of quantum mechanics, and they are used in the Dirac equation. And so, you're saying you got a solution to the Dirac equation. That made me think, well, we ought to have some correspondence between these matrices and the matrices that we generate from the Rodin maps. So I called them M1, M2, and M3, and these are the same matrices that Tony was showing earlier, except I flipped this one around. The -2 is in the upper left corner instead of the lower right where he had it. And that's important in order to get this to get this correspondence to work. I'm maintaining that M1 has a correspondence with sigma 1, M2 has a correspondence with sigma 2, which has i's in it. So how do we get that? We'll get there in a minute. M3 has a correspondence with sigma 3. So what I did was first of all, these are 3 by 3 matrices, and I want to generate a 2 by 2 matrices. The way you do that is you wrap it around a 2 by 3 matrix. I don't want to get too deep into this, but bottom line, T means transpose. So I take this matrix, which we'll recognize as the, they're the real and imaginary components normalized of the 3 points that are 120 degrees apart, 1, 0, 0, and then negative a half, and plus or minus I times square root of 3 over 2. I hope that's not losing a lot of people. Those are pretty foundational matrix points. So this is a normalized matrix. Anyway, I take that and I have the transpose of it on one side of my M, and this is the formula to get the new M sub j. Then I have to then I get the 3 M sub j's, which are still not the Pauli matrices, okay, and they're not normalized and stuff like that, but I get those 3 by applying this transformation using this formula to these 3. I hope everybody understands at least what I'm doing. Okay, and then I have a second transformation I have to do, which is related to these same vectors. It's square root of 3 and a half. We call it U and U inverse. Then I apply those to these 3 matrices, and I get the Pauli matrices. I may have had 1 and 3 mixed around, but that was my whole point, was to get from, here's how I get M2 and M3. Bottom line, there's the 3 equations. I hope this is making some sense. We don't need to get too bogged down in the detail. I'm just showing that there's a one-to-one correspondence between these M matrices, which are the Rodin maps, and the Pauli matrices, which are part of the Dirac equation. And I think that's really interesting, and maybe we can kind of put these 2 ideas together and get something a little more robust. That's what I'm hoping. So that's pretty much all I have at this point.
Hey, that's good.
You like that?
Yeah.
Yeah.
It is pretty impressive. Just to say that I think in the actual Dirac equation, they used 4 by 4
right,
matrices.
but it's
they're
like
constructed from the Pauli
and then sigmas on the
exactly.
On the side
Yeah.
So sigmas are part of it. I understand
so
that.
once you've got this, you're one step from having the full.
We may have to play with it a little
equation.
bit. Yes, I get it.
But it would be actually very impressive to write the Dirac equation using fragments of the number map as the ingredients rather than using the Pauli matrices, because the Pauli matrices Dirac basically came up with those matrices just because they satisfied the thing. They didn't make any sense. Nobody understood what they meant.
I get it.
And it's like, why do I have to spend all my time multiplying these complex matrices? And if this is another way to explain it, that could be really great. Yeah,
it might help us understand these things on at least get some new insight into what are these things actually telling us. And, quantum mechanics, just in case anybody doesn't know, even those who do quantum mechanics as a profession, they don't even understand. I mean, that's Richard Feynman is famous for saying, I don't understand it. You don't understand it. Nobody understands it. But we got the equations, and the equations work. And that's about it. So it could be that this will help us understand it a little better, or at least in a different way. I don't know. It just occurred to me there had to be a correspondence, and sure enough, there is. So there you go. Let's play with it and see where that takes us. I had some thoughts about computers if I have the floor. You were talking, and this is just me flying off the head, just totally brainstorming here, but not just computers, but what I was thinking is, the problem with the whole Rodin map thing is there's really not very much information in just one map, because you just have that one formula and that's it. And yet there is information in, perhaps if we're at let's say we're at level 1, we're at this location, but at level 2, we're within that location, we're at another location, and at level 3, we're at some other location. Then we can actually generate some information by using the fractality of it to give us something that we can deal with. And Ruadhan kind of said this, and I want to reiterate it. This is not a normal way to look at life. We usually think of things that are either discrete or they're continuous. But I think this is kind of both. Because of the fractality, we can be operating in the discrete world and yet know that it ultimately does come to something continuous, although at any given level, it's going to be just as discrete as it always was. So it's a really weird animal, but that may turn out to be a positive instead of a negative. And I've been thinking about that a lot, as how do we turn that into something useful? And, can we turn it into something that has some computing power? I don't know. Third thing I want to talk about, and this is because my background is in information theory, is one of the benefits of binary is there's not a lot of waste in, within digits. In other words, if you're only tracking like a binary choice and you have a 10-digit number to tell you, which choice you're making, then you're wasting a lot of information. I hope that makes sense. So there are some times where binary is more efficient than ternary, because if you're always dealing with, one or two, logical choices, it's a little bit of, you're adding extra overhead that you don't need. And that's something you don't want to have optimal information flow. So anyway, I don't know why I'm saying this, but I do know that the quantum computer system is, the idea is that you're having multiple things happening at the same time. And I think that somehow whatever wasted information content there is at one level is taken up in another level, so that the whole overall thing there's nothing wasted. Is that true? That's kind of my concept of it. I'm not speaking as an expert.
Do you mean in quantum information theory?
Yeah.
Yeah, so in quantum information theory, there's like a strict separation between quantum information and classical information. If information becomes classical, it can be copied, and then it can spread throughout the universe. But if it's inside the quantum system and it still retains its ability to exhibit quantum interference and entanglement and so on, then there's a thing called the no cloning theorem that says that information can never get outside of that system without destroying, as it were, the coherence of it. So you can't clone quantum information. You can only clone classical information. Maybe does that answer your question?
Kind of, sort of.
Greg,
I mean,
I'm going to ask you to stop
sharing.
sharing.
I have a fuzzy
Greg,
idea about how. Go ahead.
I'm going to ask you to stop sharing your screen, because I'd like to see Ruadhan's full face big, or your face big.
Oh, I'm sorry. Talking. Yeah, I'm done.
There you go. Okay. Now I have you in all your glory. Thank you.
Oh, okay. Okay. Well, what I'm getting at is in the quantum computing system, the reason why they're saying how awesome it is somehow they're encoding information to be extremely efficient, so that they can be doing several different manipulations at the same time. And yet, if you were to do an infinite number of iterations at the same time, there'd be no difference between a discrete thing and a continuous thing. Are you following what I'm saying? Does that make any sense?
You get a distribution of results.
Okay, yes. So this problem of a distribution of results sort of gets us into the space of where does discrete end and where does continuous begin, which was the whole analog digital thing in the first place. And now we're struggling with this kind of same issue here with this fractal idea, with a discrete system that becomes continuous in the limit, and yet it's discrete at any given level. Maybe that's going to be useful. That's kind of sounds like what they do in quantum computing systems, but I'm not an expert. Am I close to the right idea with this?
I'm actually not an expert on quantum computing either.
Okay.
I have a vague idea of how it works, but I think, I certainly hope the same thing.
Okay, well, we'll just leave it at that. It's something to explore.
Yeah.
All right, I'm done. Phil, did you have something that you wanted to go back to?
Yeah, sure. Can you guys hear me?
Yep, you're good.
Yep.
Okay, cool. Yeah, so I just wanted to, again, kind of just bounce that idea off you in terms of modeling this, so you can apply kind of the usual kind of usual models to as a particle. If we think of it as a standing wave, is that useful to start looking at the numbers as having kind of discrete values along certain vectors, so that if 9 represents a longitudinal oscillation or longitudinal compression rarefaction, and 3 and 6 are your magnetic transverse expression, and then we're looking at sort of a non-radiating boundary, valence shell as your Mobius circuit, if that's like an electrostatic field, basically. Does that get you any closer to modeling that in a useful way, or informing further application of that in existing field models? And on the subject of superfluidity, it seems to me that if there's any way to transmit information superluminally, it would require the negation, the phase cancellation of the E and B field. And I think that, at least in this circle, I think that's more well known about, and kind of the Bearden scalar interferometry thing, and E.T. Whittaker 1903. I don't know if you guys are familiar with that at all.
Yes.
So yeah, I'm just wondering, can we treat these shears as kind of geometric planes, and the functions moving within them and their interference through each other as kind of mapping the electron orbital in a way? And then does the key to some sort of quantum computing state mean the intentional phase cancellation within a system? Maybe you have a 3-dimensional space in which you are phase canceling your E and B fields and setting up sort of a tensioned substrate through which longitudinal perturbations can then occur and interfere with each other within a closed space. And so can the grid inform that? And I wonder if that can be done easily in the software you guys are already using to model these functions. Does any of that make any sense?
I think it mostly does. I can just say that when I was looking at the Dirac equation and the Klein-Gordon equation, specifically the Dirac equation, I found that the Rodin number map is not, and well, the solution to the Dirac equation that you get from the Rodin number map is not the only solution to the Dirac equation that you can define on this grid. If you look for other solutions, you can also find spherical solutions that expand or contract. You can find plane wave solutions that are not of full rank. So what the Rodin number map seems to be is it's a full rank solution that fills all of time and space. But what you can do is you can find other solutions. You can construct, for example, a wave that's traveling in one direction, or a sphere that's expanding, and that could meet another expanding sphere, and then you could study how these things are interacting with each other. Mm-hmm. But to be honest, I haven't done that. I haven't looked at how these interactions happen. What I just, my intuition is that you wouldn't get scattering. Is that if there was one sphere expanding and it met another sphere that it was expanding, my intuition is that they would just go through each other. I can't prove that. It's just based my intuition based on the fact that the equations are so linear and straightforward and simple. But yeah, I guess the question is, could you construct things that would interfere, things that would cancel each other out, not to cancel each other out, but actually cause some non-trivial interactions between the particles?
This would be like something I would think of like a force-free field of like a Birkeland current, right? Nature kind of structures these things anyway as a means of electrostatic or magnetic pressure conditions, right? And so it's kind of this exchange of energies bidirectionally. Yeah. And that, might that, and the Rodin, that's kind of, if you take that Rodin circuit, right, and kind of stretch it out, that's kind of what we're looking at, that double helix spiral. Mm-hmm. And so, right. Is the key to superconductivity and phase cancellation, in fact, geometry of the circuit. And that was interesting when you said earlier, maybe engineering a wire itself right? And so maybe we actually, you know, and I think that ultimately the hardware is really where I think the innovation is going to come in this, because you know you're kind of limited by your hardware. And so have you guys given much thought as to what that might look like? What you know, what a transistor and logic gate informed by this system might look like?
I think Greg would probably be better able to answer that than I would. I know. I'm not maybe not great, but I basically have no. I understand the basic theory of a transistor, but I really wouldn't know how to like expand it to 9.
I was intrigued by Tony's idea of you know, having a three-dimensional thing. You know, when I was learning electronics in college, everything was, you know, there was a board, and it had, you know, if you were really clever, you had two sides, and you would have to design this circuit board so that it would take advantage of two sides. Well, now we're, you know, if we're having a block with everything sort of moving around in all directions, it doesn't work that way anymore. It works completely differently. And you know, can we design a system which works without the need for metal? I mean, why not? You know, is that even possible? Can we communicate through things? You know, through waves in the air? That seems to me a next step. And there would a three-dimensional thing would make a lot of sense if we could.
Yeah,
do
I imagine a
something
bunch
like
of.
that.
I imagine a bunch of like nanotechnologically engineered molecules in a three-dimensional lattice, firing photons at each other.
Yeah, well, I think that, you know, the human body does that. I think that the cells in our body communicate with each other, you know, without interference of the space in between. You know, that I believe this is going on. The nerves are there, and somehow, and there's information carried along the nerves, but I'm not so sure that the nerves are the only mechanisms. You know, it isn't as it's happening through the space, and I believe that's going on, and somehow we could design things to do that. Then we could make some major advances, I think.
I completely agree with you, Greg, and I really actually tried to work on it. And here's what I think. I think that water is a signaling medium.
There you go.
Yes.
The electromagnetic electromagnetic signals that are relevant are of wavelength approximately 1440 nanometers, because that's the wavelength that disrupts hydrogen bonds. And water is like a weakly coupled system where the hydrogen bonds are breaking and forming on a femtosecond scale as a consequence of these you know, near infrared photonic interactions. So here's two possibilities. One is life evolved in water because water is a really good thermal regime that can make biomolecules vibrate in a noisy way so that they have the right thermodynamics to bump into each other randomly and make things happen. Another one is that water is literally the inverse of the biomolecular surface and is a continuous signaling medium that is sending signals back and forward between biomolecules. And I prefer the latter one because if you were some biomolecule, if you wanted to evolve life somewhere, would you choose a noisy channel to signal through, or would you choose one that had a high fidelity? Would you evolve yourself into a system which was able to communicate in a high fidelity way through the substrate or medium in which you were embedded? Of course you would. Yeah. And so the vibrations of biomolecules are, in my mind, they are coupled up to the photonic interactions between water molecules, probably in a quantum way, because a lot of talk about, you know, quantum biology and stuff, but not so many people have talked about about water as a quantum system. There's one set of theories about it that Ru and I have actually talked about quite a lot. He was skeptical, as I remember, but
I'm less skeptical now.
It's okay. You two disagree with each other. We're all friends.
Yeah, I mean, the water's sitting there. There are electrons ready to pop out. You know, they're just literally ready to pop out. And it just takes a little thing to send a group of them into a kind of coherent oscillation. It's a very, very rich dynamic medium. And so if you were then to contrast that with the computer, what the computer would be a crystalline deterministic system with fixed lattice locations sending stereotyped signals around, whereas water would be a continuously graded, you know, you've got all the spatial locations of all the atoms being the you know, the state of the system. And so we would still be better than the quantum computer.
That seems especially likely with Pollock's work, you know, on easy water and coherent structured water, hexagonal liquid crystals that cohere in our bodies, right?
Yeah, that's exactly where I learned that stuff. I went to their meeting once, and I talked to a lot of really interesting people there. Yeah. Yeah, that was great. That's a great community.
𝗓𝗨, go ahead with your question. It's going to take him a minute to unmute, unless he fell asleep and I'm just looking at his avatar.
Well, we're coming up on 11 o'clock my time, which is the official ending time, but we can keep going. I know Marko likes to keep going way past the end.
Okay. 𝗓𝗨, you have been unmuted. But he's still muted. Well, if you're in the chat room, if you have any questions, then say so in text, and they'll release you.
I'll just fill a little space until somebody's ready.
I'm going
to
to ask
the
the presenters to Tony, Greg, and Ruadhan O'Flanagan, Tony Bell, and Greg Volk. I'm going to ask you to give to the public whatever corresponding email you want to share. Okay? So if you want to receive communication directly with people asking questions and things like that, eventually I would like you all to collaborate together to create a white paper, because in academia, the old saying is publish or perish. And I would like, because eventually it has to be independent of us, your discoveries and information that you're sharing. So this is kind of what I consider the precursor to a white paper. Who is that to the bottom right in the corner? Go ahead, 𝗓𝗨.
Yes, hi. The system just unmuted me. 1 second, folks. My signal is bad up here on this hill. I'm going to turn off video here, if that's okay.
Sure.
Okay, that's going to be better audio fidelity.
You had good fidelity before. You leave it on. We'll tell you if it's bad.
I've done calls up here. It'll start good, and then it'll start to fade. I'm very clear on my question. It's more of an applied lab-based thing. I want to
wait. Go slow. Introduce yourself and say hi to your old camarada. Tell them who you are and where you graduated.
My name's 𝗓𝗨 𝗀𝗧. I'm here in Southern California. I called UC San Diego home in the 90s. I would be happy to return there for a conversation with you, Tony, and others. I just kind of want to come to the fore of what, you know, listening to this, as much of it as I could be present for. I want to tease something out, because I've known and had the pleasure of getting to know Marko's model since approximately 2010. But since about 2018, based on my work with a technology incubator and accelerator I founded, I have been defining what I consider a solution potentially for today's problems in machine vision. So it's a very applied area, but I just feel Marko's work has the ability to transform how we look at hyper objects moving through space-time, or however we want to conceive of it. And so I do a lot of industry analysis. I know how much Full self-driving is still a bit of a holy grail, despite all the hype and the promises and the billions that have been spent in a very narrow band approach to try to solve it, either with
I
LiDAR
hear what
or
you're
with
saying, but just talk.
computer vision.
Hold it,
So,
𝗓𝗲.
oh,
Just talk slow.
sure. I want to respect everyone's time here at the 11th hour.
We're not in any hurry. In fact, we're going to stay up another 48 hours.
With some
Speak
really
for
good
yourself.
advisement. With some really good advisement, I pulled together a standard we were putting before IEEE a number of years back called holomorphic reality capture. And the idea was to apply some of your work and Robert Edward Grant's work with some other luminaries' works to just take a fundamentally different approach, what we called 4D sensing into 3D imaging versus 2D modeling to try to derive 3D stuff. And that gets into problems of compute. And as we're seeing the AI bubble here start to burst off of the problems and limits and constraints of large language models, I just want to know if anyone had any thoughts about your work, Marko. I'm sure you do too, Marko, applied to computer vision. And I only use that term because it's the industry standard.
Except I will add, 𝗓𝗲, the reason I wanted you to be on is because I consider you an expert. Would you say you're an expert on neuroscience?
That's a very big word and a very big area to use. I would not use that word, but I would certainly say there's some areas where I have some depth of study that might be relevant.
That's also Tony's interest too, I think.
I think being an expert in neuroscience these days is throwing out the old model understanding plasma physiology from a perspective of metabiology, and what was just said about Gerald Pollack's work has a lot of the answers to what we don't understand about consciousness, the mind, the brain, and how it all structurally couples and coheres together.
Okay, what was your question before I derailed us?
Machine vision.
𝗓𝗲? I can't hear him. We lost 𝗓𝗲.
His question was about machine vision. He muted himself, so he needs to be unmuted.
You got muted again. 𝗓𝗲, you're muted, we guess. Did everyone give their email like I asked?
Should I type the email into the chat?
No, I'd rather you say it because a lot of people can't see the chat.
Okay, so my email is rof@ruadhan.net.
Again?
So ROF@ruadhan.net.
Okay, and type that in too. We'll do both.
Okay.
Okay. And then Tony, while he's typing, go ahead.
Oh no.
Your email.
I have the email. I decided to use a different email account that's not being used for anything else, just for this topic, because
yeah,
I'm worried that the whole thing will balloon and I'll be swamped in my main account. So I'm going to use the email 𝗏𝗵𝗲@gmail.com, and that's exactly the way you would think of it.
And did you type it in too? Please.
I am, but my keyboard is.
I know. And while you're doing that, Tony, Greg, it's your turn.
Okay, well, my email, I'll type it into the chat. 𝑡he.𝗏𝗀, that's V like Victor, OLKS, because it's plural. 𝗏.𝗏𝗀@comcast.net.
And because we love you, Phil, you can do it too.
Thanks, Marko. My email is phildc1, the number 1, @gmail.com.
And mine is Marko Rodin, MARKO RODIN, @gmail.com. Now, 𝗓𝗲, I really, unbeknownst to everybody, I have a question for 𝗓𝗲. So, John, could you bring in 𝗓𝗲 again, please?
I'm here. I can go ahead, Marko.
Okay. Now, forgive me, and if you have to say that you're not at liberty to discuss this. Last time I heard that, it was when Jupiter in 2001 Space Odyssey when when he was being pressed as far as what they found on the moon, the monolith. You know, if you can't talk about the monolith, it's okay. But I think it'll benefit very much Ruadhan, Tony, and Greg and Phil. Can you discuss, is it true, tell me if I am wrong, that a very different variation, Rodin coil, and everybody's waiting on pins and needles to go into the field of free energy over unity, or using the Rodin coil as a harmonic filter on existing power plants, electricity and transformers. Is it true that there's been instances where there's been a 1/3 plus savings on electrical bills in the millions? Don't get anybody mad at you. Just forgive me for putting you on the hot spot. What do you have to say on that topic?
That question was for me?
That was for you, 𝗓𝗪, because you have a company and you founded it, and with your other principals and friends and engineers under your umbrella. So is there an application that you're familiar with that you can discuss where the Rodin coil has direct applications to hardware and power generation and efficiency? Huh?
Yes, I am aware of some. Yes, I don't believe I'm at liberty to discuss just out of respect for an NDA, but also the parties involved are very accessible, very friendly. Actually, here in Southern California,
You're talking way too fast again. I'm sorry. We're going to have to slow this down
I can
like 40
understand you.
times for us to understand what you are saying. It's like your mumbles in Dick Tracy, okay? And then
sorry, on your end, it's different.
It's,
Yeah, I
well,
was simply saying the folks involved are very accessible in your community, Marko. You're welcome to call them out.
Okay. And
I mean, I can talk about it. I've observed some things. I think the technology is real. It's doing what it's supposed to do.
please, anything you can say, I would be very grateful for. It's kind of like Jupiter and Beyond, the 2001 Space Odyssey. It's reached a whole new level of abstraction and psychedelics. But what do you have to share?
Sure. Their best, this is public knowledge, the part I'm mentioning. Their best application thus far is in data centers that are typically going to be used for AI. And they're offering 20 to 40% savings consumption. Everybody knows it's starting to become a matter of legislation and challenges at the state level nationwide.
I'm going to interrupt you. You've said enough. Now you are one of the presenters. You can give out your email and you can keep everything else in confidence and in private so that you don't have to tip your hand and qualify anybody that you discuss it with further.
I'm going to type my email here in the chat, folks. 𝗓𝗪@gmail.
Spell it, please.
It's in the chat.
I know, but we don't have.
I have too many vowels. 𝗓𝗪, all A's. Every vowel is an A.
All right. Is anybody trying to get my attention? I am Robin. Okay, Robin, come here and take the mic, and when you're done, give it back to me, please.
Aloha, my name's Robin, and I'm the founder of the Global Freedom Alliance, and I have an evolutionary education show. And one of the most important, shall we say, free energy or exceptionally new energy sources to the public is also using Marko's map. And it is proven. I'm just not able to talk about the company name at present.
Let me think here. Where were we? Okay, Lisa, I'm going to do something responsible. I'm going to actually, without ending and without closing, say anyone who wants to sign off and recoup and has other responsibilities and commitments, I'm going to do a quick closing. Lisa, are you there? Could I see Dick Tracy, please? How about the link to that website? We've been doing this all on the fly. And I want to thank our guests. And I think that this is, as we all know, forgive the pun, what you're doing, what we are all doing, is the tip of the iceberg, as we all know. I know that we all feel that we're in very, what we call, blessed company, okay, to be able to rub shoulders together and to be in each other's presence. I'm very grateful for everybody's contribution and efforts and sacrifice. We're all paying out of our own pockets to bring this to fruition. The author of Dick Tracy, when he did that little watch right there, if you see written on the bottom, it says, the nation, he was doing the recorder watch, like the Samsung watch or the Apple watch. It was turned into a phone and a radio and anything. And now, of course, that's conventional technology now. It's the norm. And this is over practically 100 years ago, give or take. He wrote in the bottom of the caption of this image, of this cartoon, on the sidebar. And that's where all the most important notes are, is in the sidebar, as we all know, in historical breakthroughs by the founders of physics and engineering and science and cosmology. He wrote, the nation, but it's not the nation anymore. Now it can be any one of you. It can be Greg, Tony, Ruadhan. The nation that controls magnetism will control the universe. And I think that the Rodin toroid number map, which I call the Decoqubit, is the secret of how to focus magnetism, okay, like a laser, okay? And the applications, as we know, as Russell Blake from Microsoft, department director of advanced operating systems said, where do we go from here? Because he has written hundreds and hundreds of pages on vortex-based mathematics, which you all have copies. And he said, literally, the sky is the limit. And that's how I'm concluding it. We can continue if anybody wants to continue, but maybe we'd be smarter to rest. Greg, I'm going to ask you to redo your paper for 𝗏𝗏 next week. I'm going to ask Tony and Ruadhan to stay on this with a white paper till you're happy that you've got it polished and refined to where it's doing your bidding and you have control of it. And go ahead.
Can I make a request? If you would be so kind, I would really like to see the presentation you did tonight. If you could forward that to me, I just want to get the core ideas. I think I got most of them, but I want to be able to reproduce it. All this stuff about I pretty much have the Klein-Gordon down. I don't quite totally.
Lisa and John heard you, and all the speakers will get a Google Drive link to download the entire presentations for Tuesday, Wednesday, and tomorrow night, Thursday. So no problem. Okay, that'll be done.
We're both pretty busy until December. Ro and I have a plan to meet in December. Probably we should write it up.
Well,
but probably there's a few things to fix.
You mean it's not going to be ready by tomorrow morning?
Well, you can have a crappy version. I mean, I already
this is you know, everything needs a deadline or nothing gets completed and done. But the truth is that it's the ball's in your court. We're just all standing here on pins and needles, you know, but we're very grateful that for this presentation tonight, because how do you believe that this is going to transform quantum field theory? I'll ask Tony.
Oh,
hello,
well,
Tony.
Actually, I will say, actually, this is not a direct answer. You have stimulated us into thinking about this when we let it lie for 5 years, basically, over 5 years. And since it's only, I don't know how many days it's been, 4 or 5 days, I've already thought of some other things that I wouldn't have thought of.
Speak a
5
little
years
louder
ago.
for me, though, just because I'm having a little trouble hearing.
Yeah, I've thought of some things that I wouldn't have thought of 5 years ago, because 5 years ago I didn't know those things. So I've revisited the idea with some new knowledge that I didn't have then. That means that I'm going to take it in a new direction with Ruadhan in December. And I think we're going to go through another iteration on this stuff like we did in 2019. Ruadhan's a lot more busy, but at the same time, I'm a lot more savvy on on some of the things than I was back then. So with his help, maybe we can turn it into a completed piece of work that points more clearly towards the application.
And if I may,
I think it would be a physics paper, really. You know, it would be firing into that group of people that think about the foundations of physics. I think that's where it's been heading. What do you say, Ruadhan?
I agree. Yeah.
Since you're at UC San Diego and it was part of the original question, have you had any reactions with Brian Keating around any of this, since he's hosted people like Eric Weinstein in his geometric unity
no,
work?
I haven't been in San Diego since, you know, I finished working there in the year 2005 or so. I never met Brian Keating or any of those guys. And at the time I was working in biology, basically, and machine learning, and I wasn't really interacting with physicists. And except for Ruadhan was a physicist who happened to be upstairs in in Chuck Stevens' lab. So yeah, Ruadhan was the physicist at Salk.
Understood. Maybe the same could apply. Have you all explored and paid attention to Eric Weinstein's work?
I looked at it a little bit. I noticed, of course, there's a big a fight online about that stuff.
Yes, quite a.
Well, some people were really horrible. I don't know. I find him interesting to listen to be honest. But geometric unity, I didn't go through it in detail. People attacked him for not having a Lagrangian in his paper, but there's like Lagrangians all through the paper.
He did. He had a whole section on Lagrangians. No, I did
don't know
read
what they're talking about.
I
mean,
did read through the paper. Yeah. Sorry, go ahead.
In that whole world, there, you know, everybody's failing. So it doesn't really work to sling mud at people. Everybody's failing, you know.
Yeah, I think he has antagonized the string theory community, essentially by perhaps accurately accusing them of strangling theoretical physics and saying, you know, every theoretical physicist in every university physics department has to be a string theorist and so on. Yeah, I think he's not liked, I think, by the string theorists. But I did read the geometric unity paper. I can't say I read it in so much detail that I understand all of it, but I do understand what he's trying to do. And what he's doing is he's taking these ingredients from physical theories that are incompatible and taking the principles, but kind of fitting them into one another without building a full theory, finding out how they fit into one another in such a way that they can't be disentangled and that they do actually, you know, fit correctly together. Like, say, for example, he'll say, oh, we need 10 numbers to plug into this. Where do we find these 10 numbers? Oh, they're in the metric. And let's take the metric tensor and we'll take 10 numbers from there and plug it in here. And then the result is he's got a system that describes the geometry of physics, in which it can't, the contradictions between these different theories can't appear because he's kind of welded them together at the very most basic mathematical level. And I think that's it's a great idea. I've never heard that idea before, and it's a great idea. The thing is, though, it doesn't get you all the way to having a fully quantum theory. It's not actually a quantized theory. It's rather a description of the geometries that are involved in these different theories and how they can be put together and made into a unity, a geometric unity, which is a good title for it. But from from the point of view of like a mainstream physicist, they would say it's not a full physical theory. It may be a description of geometrical unity, but it's on its own. It's not full physics, or it's not predictive, for example.
Stephen wants to say something.
Is this thing on? Okay, yeah. So a little bit on my background, because a lot of people here don't know what my background is. And I will humbly say I have no way the credentials that you guys have. This is not even close. But one thing I have been doing for about 35, 40 years, I worked in the research and development department at an aerospace place at a high level of tinker level, if you will. So I rubbed shoulders with people like you, the engineers, physicists, electrical engineers, and
What aerospace or corporations?
originally it was the McDonnell Douglas Corporation in Huntington Beach, which ended up bought by Boeing. It's the only facility that McDonnell Douglas had that was in the black.
Works.
And they did skunk works, they did, DOD work. My particular job and function was ground support for Cape Canaveral and Vandenberg Space Systems. We worked on space station, space shuttle, and lots of hardware. I mean, it's kind of cool knowing my hands have been on stuff all over space. But it led me into an interesting thing through the whole gamut of this. I've always been an armchair tinkerer in Tesla technology, alternative sciences, and understanding physical stuff. Meeting Marko and the toroidal thing, I just see so much potential. But also through this whole thing, I've done a lot of spiritual work. And this is something to consider in physics, I think, from a perspective. We're this human condition called the human being. Now, mind you, all of us are on this planet and we're human beings, and we've been trying to figure out how things work for millennium and millennium and millennium. Now, think about this. All we have is a limited bandwidth of vision, a limited bandwidth of hearing. Our physical shape, it can only deal with so much stuff. It begs the question that when we try to understand physics or our physical world, even the way we think about it is been always modeled with a limitation of our condition. We can only think so much, we can only see so much, we can only hear so much. And I love the equation of what Einstein said. God doesn't play dice with the universe. And I love it when Stephen Hawking said, not only does he throw dice with the universe, he throws them where you can't see them. So the question or the postulation or the end result is here, it's such an honor to be with people that think out of the box. I mean, that's the real heart and the meat and the intention of physics and in-depth electromagnetics and all this stuff. And I'm a very physical person. I can look at something and, oh my, I see something. But interesting, I mean, if you look at a toroid, we're only talking about one closed thing. I mean, what if that track of that oscillating vibrational thing just starts processing in a different way? It could get fractal, it can turn into a Mandelbrot, it can go inside, it can go outside. I mean, this is cool because maybe it's the foundation that makes things happen in a manner that we can actually identify physicality. But man, I'm so glad to see people like us willing to think out of the box, to think one more step, one more vector, one more incident, one more propagation. This world wouldn't work if we didn't have people like you doing this kind of work, to dare to think the impossible, and to eloquently learn and get incredible disciplines to try to model and explain this amazing world. I stand in with giants. I mean, I make stuff. That's all I do. And I get the ideas and I try to play and tinker with it, and I just love it.
At San Diego State University, I met with the most advanced mathematics teacher for the aerospace, where they teach math where everything has to be elastic. And his name was Mario Perucci. Stephen, hold up. This is really for you, Stephen. I'm trying to prime the pump. And When he looked at my God's light cone, my funny VW symbol, and by then I probably had the toroid number map too. We're looking
Yeah,
up there on
you
the
did.
screen. He says, I know exactly. I met there with the dean. I met with every. It's just amazing the support that they would even meet with me and give me the time of day. And he said, I know exactly what you're doing, Mario 𝗶𝗶𝗴𝗡. He says, you're making a nozzle. That's all. I'll say it again. He says, you are making a nozzle. Now, Stephen, and of course, I'll just keep it brief. It's all about space-powered propulsion systems, how to make mankind intergalactic citizens. I believe that this discovery that you are explaining, that we are all working. By the way, Phil, are you?
Yep.
Tell me some of the engines you can repair in aerospace. Are you an aerospace mechanic?
No, I had some training in that field, but I decided to be a thrash drummer instead.
That's what I thought. You heard it direct, and you were there too. And in this day in history, October 8th, 2025, that Phil threw it all away, and his parents have never forgiven him. Okay, it's to be a drummer. Oh, but Steven's a drummer.
Yeah, I'm
too.
a drummer too, so I totally relate with Phil.
So this nozzle of toroidal pinch, the primal point, the hourglass, it's called the what? I forget, the vertex? Can't remember. This is the third point, in between compression and decompression. Makes mankind intergalactic citizens. I want to make it as an electrical venturi. I don't want solid state rocket propellant. I want a solid rocket propellant. I want to make it out of where there are no moving parts but the subatomic particles themselves, where it creates a localized space-time implosion. It's the ultimate. It would make mankind intergalactic citizens if you can turn those circuits into the ultimate nozzle, the ultimate hourglass.
Stephen,
Yes,
is there a secret space program?
absolutely. So, but he's on to something. The toroid is the answer to this.
Explain the toroid to us, Stephen. How
Well, think about it. I
Hold it up,
I
real-
love,
and
I
talk
love,
real loud.
I love the shape of a toroid because one, obviously, it's very eloquent. It has an inside surface that's infinite and an outside surface that's infinite. It never stops and it never ends. But what I look at and when I see, let's say that surface is a boundary condition of a coherent event of something moving in space to counter space. And it creates this shape in spite of everything. It's something got it to become coherent, to shape itself into a donut, if you will. Now, I equate the surface of that would be almost like the Schwarzschild radius on a black hole. You got internal implosion and you got explosion on the outside. And the interesting thing, if it's processing, because it's moving into the middle, and I don't know if you can see that on the.
I can't see it.
So I'm holding it up right there. You see that red line on there? You see the red line on this model here that I'm holding?
Yes.
That's like a figure eight. That's that W that you see on the Rodin diagram. So at this point in the center, it's not actually touching, obviously, in this model. But depending on the dynamics of the outer diameter, the inner diameter, and that pinch point could be pretty much any size, to the point that it would almost be the equivalent to, like, I know if anybody knows what a Hilsch tube or a vortex tube is, where the air swirls in the middle. And they have the venturi is tapered on one side, straight on the other. If you drive air into this vortex tube, hot air goes out one air and cold air goes out the other. Well, that denotes a magnetic pole too. I mean, if depending on the direction of precession, you got a dipole. Now, my idea, because if this stuff is holographic and scalable, all the way down to electrons, protons, and neutrons, they might be bipoles. Maybe we're trying to separate charges, and when technically all they are is movements and moments. I mean, I laugh. I don't know that much about physics, but I know when a particle accelerator does its thing, the propagation of whatever they find only lasts for seconds, and then it deteriorates into whatever it deteriorates to, and then it's gone. Maybe all that energy and that potential moving in a wave function, electromagnetic or whatever, dissolved back into the counter space where it came from. This is just coherent. That's all it is. So if that's the case, what a perfect thing for you might say a electrogravitic device, because you can have, it's a thrust vector. You got a nozzle, as what Marko's saying. When I saw that, I just couldn't believe it. But obviously, how do you wire it? How do you design it? How do you engineer it? I mean, you're talking some serious potentials of energies. I mean, look at it. It's a tokamak. I mean, it's the same principle. They're running plasma in a circular thing. But what maybe that's not the idea. Maybe the idea is the implosion explosion, and this is a boundary condition. So there's so much engineering going on here that I see, that I bet you. I mean, look at a TR3B. What do you see? It's laugh because everyone's saying we made them, they made them, who knows, whatever. But you got three dots and a big dot in the middle. Well, interesting, when you make these toroidal coils and you lay them out on a plate like that, all the magnetic structures, they're processing within each other depending on the energy. If that was the case, I got a gravitational ability to put less energy, right energy. That is a vectoring device to cause motion and direction. I laugh. I mean,
these things seem not to obey the laws of inertia, right?
Yeah. I think there's inertia.
It's hard. If I believe that, then I always want to see some kind of decoupling from space time or something.
Yes.
Occurring, such that you create a local scenario of your own and just bounce around in it.
Yeah, so I see all this. Some of the stuff I can't even understand myself. All I know is I know there's something there. It's just it's screaming at it. Now, not only that, you got all those number maps, and they show all these elegant spirals. Now, depending on how you make those maps, the spirals will get more tight, more loose. I mean, depending on the geometry, now you can model probably every element in the periodic table just by changing geometry on these darn things. Another thing I see is, if that geometry can change like that, it would change the dynamics and the attributes of what it does physically. So and not only that, Marko likes putting the coil on the outer surface, the boundary condition. This coil right here has a complete different kind of a wrapping on it. It'd be too hard to explain right now, but again, how you wire it. I mean, are you going to lay it on the surface? Are you going to make it vertical? I mean, and what the processing angle is, if you're going to have multiple tracks. I mean, there's so many things that need to be researched. So many things.
One of the things about this coil, which they named the Rodin coil, we've been talking about the same number map, but when I talk about a computer, I call it the Decoqubit. When I talk about it as a nozzle or as a coil, I call it the Rodin coil. They named it, not me. Let me concentrate here. The coil, all coils for motors today create a toroidal field. There is a big difference between this coil, because it does not produce a toroidal field. It produces a poloidal, P-O-L-O-I-D-A-L, a field, okay? Most people, have not heard or understand why this coil is so different, its field, the poloidal field. The poloidal field with these windings are a very gradual slope, the windings, because they're going around in spires, and it's a very gradual ascent into the vortex well, the funnel, the well. It's like driving in San Francisco on that huge hill. That's a toroidal. It would be, the grade would be so steep. That's not what this coil is. This coil is a very gradual slope, okay? And it produces a field. A toroidal coil has a field towards the horizontal. This field is towards the vertical because of that gradual slope. You get more compaction, hexagon close packing. You get more condensed. I'm not doing justice to it, but I'm just sharing with you that this is a different animal than a conventional coil. Let me see if I can remember the last thing I wanted to say. It's a poloidal field. I have one last question for all the panelists. Phil, you're everybody's avatar since Greg had to go. The question is, when you look at the numbers over the surface topology, I know we have 3 maps and you've combined them in 4D and etc. My question is this. I'm familiar with fundamental Newtonian physics, Newton's cradle. I know when you drop one ball, and I know the explanation is elastic, and when it hits another ball, and there's heat released. By the way, I consider the torus a heat sink. I consider it maintaining itself at constant temperature. That's its function, to sustain itself through respirating and in and out. But my question is this, and tell me if I don't phrase it well, because I want a very exact answer. If any number is not moving and every number is a stationary vector interstitia, if it's a standing wave or nova or whatever, and all those numbers are connected right, left, front, back, up, down, and higher dimensionally, and I'm thinking even much higher than 4th dimension. I'm thinking omnidimensional. Back to the question, if all those numbers have a right, left, front, back, and they're not moving and they're stationary, even your HAL 9000 AI, ChatGPT said, the numbers aren't moving. This is a frozen, it said frozen. Did it say it? My question is, what's being passed through those numbers? Is it momentum? Is it force? Is it communicated agitation? Is it a shock wave? Is that a fair, is my question even grounded in reality? That's my question.
We're all asking that question. That's the #1 question I'm always asking about this thing. It's like, how is it doing anything? I think the answer is, we don't know yet.
Well, if there's a hidden force there, then that force can be tapped into as a wellspring.
Yeah, I think we're missing something. I think we're missing something.
Then we can go anywhere in the universe with this once we harness it and tap into it and never have to return back to Earth for fuel. This makes mankind intergalactic citizens, because you take this in a briefcase anywhere you go. And if you tap into that, okay, what is yelling and screaming in plain sight that there is
so we should work on it.
Yes.
You have been, and you've done a marvelous job.
Something going,
and I'm so thankful that
something
I'm jumping
going
in your lap. I'm going on vacation right now, and I'll see you. I'm taking a Norwegian cruise ship around the world, and when I get back, I expect you done.
No, it is actually it's a remarkable and anomalous situation that most people could not bear. we're actually the subset of people that can bear the fact that something which is completely frozen.
I want you to break.
is-
I want you to break the computer. Break
is
break
nonetheless
AI.
like
Break
something
Chat
it's
GPT.
very dynamic, and it and we can work on it and find out all its properties, and with some kind of faith that there's some idea that we're missing that will bring this thing to life, like Pinocchio, make it into a real boy.
I could say this because of working in the idea of people like you would come in the shop with a napkin with an idea on it, and they say, make this. This work, this peer review paperwork, you might say probing this thing ad infinitum is going to give the opportunity and the end result information for somebody like me that tinkers and saying, oh, I see that. That's what the information is going to help. Oh my God, there it is. It's right here. That information is going to stimulate the fabrication and the manufacturing and the research and the development of how to apply this thing. That's what I see. Because I mean, you guys are in that world. I'm in the world. I'm seeing stuff right now I got to go do now. Just by what little information we've shared here has got my mind going a million different directions. So like that, I think that's where the marriage it is. And I mean, even when I worked in the aerospace industry, it is probably a lost art. Some of the people I worked with that had such skill and such ability, and that's not handed down. It's so sad. I mean, the engineers that help stuff go to the moon, the Apollo program, that those manufacturing RD people just don't exist anymore. They're operators. They run up in the computer, they give them a program and they run it. To actually make the stuff on hands, bench machining, massaging and making this stuff, the information how to make miracle stuff is going to come from the individuals like yourself, working this stuff and giving the ideas and then going into the RD lab and bringing it to life. That's where this is going to really, really make a big explosion as far. That's what I see.
Okay.
Yeah, I think it would be great to you see, we're already getting something a little bit like we're writing programs and they're going into a language called CUDA, and that's getting sent to the GPU in these things called kernels, and it's getting spread out through 10,000 things, and the thing's doing I wrote some code recently. It does like 600 million geometric operations a second in projective geometric algebra space. Like, you know, if that turns out to be a modality, that particular kind of mathematics for computer vision, like 𝗏𝗏 was talking about, or anything else in engineering, then the GPU will be redone in a couple of years to fit the algebra. So I do think that there are answers, there are algorithmic, mathematical, algebraic answers to questions, and once you have them, the research is over. You know, people go on to work on something else. Right now, we have AI working in a very weird way with a very weird set of neural nets called transformers, which I understand pretty well, actually, and they can be improved 1,000 times probably just by within the current paradigm. But if you shifted paradigm to a system that was like some kind of three-dimensional box, Rodin computing device, it would just be people would just build these cubes, and I don't know, we'd be in the Diamond Age, you know, like you read that book, The Diamond Age, by Neil Stephenson. Yeah, I think that there'll be some incredible advance, especially with the AI. We'll be charging ahead now, I would say. I'm more worried about society than I am about the future of technology. But that's another story.
I don't want to say the last word. Who wants to say the last word?
Just real quick, I dropped a couple images in the chat, just on the subject of coherent number grids. There's a whole realm of Marko's system that integrates with phi ratio stuff, and so I stumbled upon this thing. I don't know if you guys can see that in chat. Greg Volk informed me that I structured those formulas incorrectly, but probably close enough for you to see what I was shooting at. But take a peek. You'll see all Marko's functions there, and that red sequence actually also describes.
Oh, did you ever fix your screen share?
Yeah, I think so.
Because I don't see your screen. I don't see it.
Do you not see me at all? Am I not on?
I see you, but not your computer.
Oh no, I haven't. Yeah, I'm not trying to.
Okay, well, I was just reminding you.
Yeah, but just I just don't know if you guys want me to email that to you, but just something to take a peek at. Maybe.
Yeah. Can you email it to me? I'll have a look. Yeah, I was interested in the golden ratio stuff.
Yeah. So Tony is 𝗏𝗏temp@gmail.com. That's correct.
Yeah, that's right.
And what were you, Ron?
It's rough@ruan.net. So it's two steps above Tony's email in the chat.
Oh, okay, perfect. Okay, yeah, I'll send that to you guys.
Fantastic.
But
thank you.
yeah, I think there's a lot there. I think whether it's I do think there's something I know we're trying to close out, but the kind of cancellation of the whole system equaling zero is very interesting to me. And I think I think the 9 is the key, right? The 9 is the canceled system. That is perfect coherence, perfect balance. So I do think the key to any kind of quantum linking or anything like that is the 9 is gonna be the primary fulcrum through which that occurs. So anyway, I really appreciate your work, guys. That was fascinating. Really kind of reinvigorated me on some of this stuff. So, looking forward to whatever you guys get into, and I'll kind of send you some of my materials, and who knows, maybe it'll spark an idea one way or another.
That sounds good. Looking forward to it.
Yeah.
Until we meet again. Good night.
Tomorrow, right?
Yeah, so, well, that was at the end of Dr.
Today.
Strangelove. We will meet again. Don't know where, don't know when. Tomorrow night, I'm going to be from 5 to 7 p.m. Arizona time. Then there will be Randy Powell from 7 to 9. He sat through this whole conversation tonight. He wanted to make a few comments, but he had to go before we were able to open up the chat room. So we'll see him tomorrow night. He's going to address primes a lot. He did primes into the thousands, squaring them, always making a hypersphere. I do want to point out again, I guess that's my privilege as being the founder or discoverer, is that, but it was really done by Thorpe. I did base 10. He did all the higher dimensional prime bases. And what is remarkable to me, this is my getting in my last 2 cents, is that the number of circuits increase based on the prime number squared. I know Ruadhan mentioned that you're adding another dimension of time, and this may be spurious, okay? Randy has thoughts, Greg has thoughts, Tony has thoughts, Ruadhan has thoughts about every time you increase a prime after 3 squared. But what is remarkable to me is that 5 squared, which was Mod-9's base 26 that he mentioned, it has 4 circuits or 2 pair of circuits. Remember, these circuits are closed circuits. They're not unbroken. They're unbroken. Okay, these are true circuits. Okay, counter directional. Okay, so we have 2. And what I've asked Randy to talk about tomorrow is really important to me, and he'll do it in his head. You'll have a lot of fun watching it. He'll tell you what the multiplication series are, because you're no longer in base 10, you're now in base 26. So of course, as Greg was doing, 11 is really 10A or 10B or 10. I mean, you know, we have to create a whole, even Thorpe, who made the discovery, had to create a nomenclature for a higher base system. You guys know what I'm talking about, of course. So, but my point again is one pair of circuits, base 10. Two, which is a 3D toroid number map. Base 26, because it's a prime squared, which is 5 squared, next prime in succession. 4 circuits, 2 pair, okay? 7 squared, base 50, mod 49. How many circuits? 6 circuits, 3 pair, and so on up. That's amazing to me, because all of a sudden, prime encryption, which is used in all finances, suddenly looks like it's easily decrypted, okay, when you're thinking 4D, 3D toroid number maps. Forgive me, I'm just seeing a pattern. And what is remarkable to me is, as Ruadhan was mentioning, after base 10, we've been doing 396, 693, but it's really into the volume of the torus. It's really not over the surface. It's really not palindrome, because it's really tangential or perpendicular or orthogonal, the 396, 693. But what is going on is in 5 squared mod 25 base 26, and now as Ruadhan was mentioning, we now have we now have 10, 5, 25, 50, it's that flux field, I call it a flux field. It's invisible. I leave it alone. I don't put anything there in that gap space. I call it the equal potential major groove gap space. That gap space gets longer, but it never gets a tile wider, okay? And these toruses, and now it's doing more circuits, and they have shears and boundaries, which we each have our own idea about these shears. I have mine, how they're a harmonic boundary that insulates, that doesn't require rubber or shellac when this thing's being made into a machine, a motor. You have 2 wires, 2 conductors, except I don't even think that's truly how it's made, that naturally insulate, that it doesn't short circuit out. And Andy tomorrow night's going to talk about the multiplication series for these new pair of circuits. Thorpe did it. He mapped it. And if I can, tomorrow night in my presentation, I'll bring up his original pictures, if I can finish my presentation tomorrow during the day, and I'll show the original discovery of these higher prime squared toroid number maps, and Randy will explain it all. And with his own opinions, he has his own thoughts, his own opinions, his own conclusions. But why am I mentioning all this? Because I'm mentioning what is remarkable to me. I'm mentioning where I see new data, new structure, new patterns, okay? Which I always equate to a coil in the physics, 3D, yeah. That it's real, that it's an actual structure. So that's the plan for tomorrow night. Thank you for asking, Tony. Thanks very much. See you all tomorrow. John's saying thank you. He's saying he's got to put out the cat and dog.
All right.
He's got to put out the cat.
Well, hey,
we need to sleep.
Yeah, I do as well. It's been great talking to everybody. This has been fantastic. I'm looking forward to tomorrow night. It is 6 a.m. here, though. I think I'll need to get some sleep too.
Thank you. Good night.
Yeah, that was great. Thanks, guys. Thanks, Marko.
Yeah. Take care, everybody.
Bye, everyone.
Bye.
Bye.
Bye, everybody.
Thank you, Marko.
Recording
pleasure.
stopped.
Thank you, audience.